कितना कौन करने वाला है?
गोपाल।
गोपाल ना?
देख अभी देख कैमरा सेट करके देना भैया। देखो मैं ये तो सही। इस दिख से फेस दिख
ये सर हाँ चाहिए स्क्रीन है सर।
हाँ 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 फेस सिर्फ फेस उधर रखा तो थोड़ा थोड़ा ऐसे प्रोफाइल भी आएगा। इसमें जूम आउट हो सकता है। लगाओ
यहाँ पर
कैसे रखें?
खड़ा कर सकते ना किसी से। अरे वो स्टैंड लेके आ गया। कौन सा? वो ट्राइपॉड स्टैंड। ये नहीं लगेगा सर। इसमें कुछ कर देंगे ना। इसको ऐसे घुमा के रख देंगे। ठीक है उधर रखा हुआ है पोडियम में रखा है। अभी आ रहा हूँ। कौन सा बैग रखा है? अभी दिख रहा है? इसको टेप मार दे। टेप टेप मारेगा इस पे गंदा लगेगा।
एक इसमें आराम से
इधर वाला
हाँ उसमें करेगा ना
सर दिख रहा है इसका। सर
अभी हाँ अभी ठीक है। पर ये देख जूम में आएंगे।
टेप लेके आओ। नहीं रहने दो कोई जाएगा तो मैं डबल टेप लेके आता ना।
हाँ स्टिक कर दे
बेकार हो जाएगा तो।
क्लास में कुछ और लेकर आना।
ये देखिए
स्टैंड ट्राइपॉड भी लेकर आओ इसके लिए। ट्राइपॉड भी लेकर आओ।
चिपक गया।
श्रुति श्रुति एक मिनट
डबल टेप लेके आएगी। अरे हो गया ये देख
क्लासरूम से।
अरे ये हो गया रे
उधर
ये देख अरे ये ले हो गया।
काका से मांग ले। और एक और चीज ट्राइपॉड है ना क्लास में जो कल मेरा लेकर आया था वो भी लेकर आना।
ले ले
इनके पास होगा टेप
यार। अभी दिख रहा है ना? देख हो गया।
गोपाल तीनों से चेक करके रखना।
दूसरे प्रोफेसर आएगा तो मिनिमाइज करो।
हाँ
इधर
इसका प्रिंट आउट है ना
प्रिंट आउट ये सेव नहीं हो रहा है इसमें बेकार है।
थोड़ा क्रॉस लग रहा है थोड़ा सा ऐसे।
अनिरुद्ध सर भी है। अनुपम इसको वो साइड स्क्रीन करके रखो। क्यों स्क्रीन वो साइड करके रखो जब तक तुम लोग का चालू है।
उसका बाकी इसका
डाउनलोड नहीं हुआ है।
हुआ है, डाउनलोड करके रखा है मैंने।
नया वाला डाउनलोड किया है।
हाँ, नया वाला डाउनलोड करके।
मैं लेकर आया। एक हो गया सेंटर में खड़े रहेंगे। अभी देख सेंटर में खड़े रहेंगे। ये लगा लग गया है ना। बड़ा लिख
काटना पड़ता
कैसे काटेगा नहीं वो निकाल कौन बोला देखो आए तेरी मर्जी। नहीं तू दिख नहीं रहा है। अरे ये YouTube का देख रहा है तू नहीं लेट लाइव स्ट्रीम। हाँ लाइव दिख रहा है कि नहीं? हाँ यार इतना यहाँ से कैमरा का हाँ ठीक है चलेगा। आ रहे हैं थोड़ा जा तू नहीं लेकिन हमको इसको थोड़ा हाँ थोड़ा ये उठा दे ऊपर से उठा दे नहीं तो बहुत ज्यादा उठ रहा है। तू सीधा स्टैंड पे खड़ा गलत पोजीशन। हाँ मैं बैठूंगा इधर ही बहुत नजदीक है इसको पीछे रखना पड़ेगा। सही इतना आना चाहिए उतना तो आ ही नहीं रहा है। रुक फेस आ रहा है चलेगा या फिर इसको ना यहाँ पे चिपका दे। एक अरे ऐसा है ना पूरा ओपन होता है ये ना तो खड़े रहे ना और इसको ऐसे रख होता है क्या वो रुक जा नहीं होगा नहीं होगा ऐसे नहीं होगा ये ऐसे नहीं हो रहा है ये इतना ऊपर की तरफ ही नहीं होगा। ये ऐसे ऐसे रुक जा मैं यहाँ पे ऐसे और ऊपर हाँ नहीं ऐसे 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 ये इतना ठीक है छोड़ नहीं बस और भी दूसरा बस बस इनफ है। तू खड़ा रहे फिर तो काला ही है नहीं एक मिनट अच्छा वैसा भी सही है। हाँ बस खड़ा तो वाला से कुछ अरे वहां पे हाँ ऐसे थोड़ा हाथ पे ओके दिख रहा है, ये भी कवर हो रहा है, बनाया ना इसलिए। इससे सीखना है बोला मैंने ऑटो इतना सच नहीं। हम लोग ने टाइमर में सेट किया ना स्लाइडर ने सेट नहीं किया, उन्होंने किया क्या टाइमर ट्रांजिशन उसमें सेट करना देना ना।
2 minutes का 10 seconds का 15 seconds
हाँ चलिए
20 seconds
पर वो कंटिन्यू आफ्टर
20
10 स्लाइड है। इतना लंबा थोड़ा चेक करने के लिए मैं सेकंड करता हूं। इसके बाद ये वाला इसके बाद
फिर से लूप में लाना लूप में फिर से रिपीट करने के लिए हमारे सेटअप लूप कंटिन्यूअसली
Everyone, please settle down. Respected dignitaries, esteemed academicians, invited speakers, and dear participants, a very good morning to all of you. It is with immense pleasure and academic pride that we welcome you to the National Conference on Computational Geometry, Analysis, and Machine Learning, jointly organized by ICT Mumbai and S.I.W.S College. The conference features a vibrant blend of invited talks, contributory presentations, panel discussion, poster session, and a culture program, culminating in a valedictory function. It brings together researchers, academicians, industry professionals, and students for a rich and insightful exchange of ideas. Please join me in welcoming the distinguished dignitaries for the inaugural ceremony of NCCGAML 2025. I now request Dr. Ajit Kumar, convener of NCCGAML 2025, to kindly accompany our chief guest to the dais. Welcoming the chief guest, Professor Dipendra Prasad, chief guest of NCCGAML 2025, chairman of NBHM and Emeritus Fellow of Mathematics at IIT Bombay. Welcoming the keynote speaker, Professor Anirban Chakraborty, keynote speaker, Professor at the School of Computational and Integrative Sciences, Jawaharlal Nehru University, New Delhi. Welcoming the honorable dignitaries, Professor Aniruddha B. Pandit, Honorable Vice Chancellor, ICT Mumbai. Shri R. Radhakrishnan, Chairman, S.I.W.S College, Mumbai. Professor Manali Londe, Principal of S.I.W.S NR College, Swamy College. We are honored to have their support and gracious presence on this academic occasion. As a mark of our deep respect and heartfelt appreciation, we now move to the felicitation of our dignitaries. We humbly request the presenters to come forward and felicitate our distinguished guests with a sapling, a memento, and a special souvenir present on the table on behalf of the organizing team of NCCGAML 2025. May I first invite Honorable Vice Chancellor Professor Aniruddha B. Pandit to kindly felicitate our chief guest, Professor Dipendra Prasad. Next, Professor Ajit Kumar, convener of NCCGAML 2025, to kindly felicitate our keynote speaker, Professor Anirban Chakraborty. Now, Professor Hema Sundar, co-convener, to felicitate our Honorable Vice Chancellor, Professor Aniruddha B. Pandit. Followed by Professor A.R. Bhaumik, ICT Mumbai, to kindly felicitate Shri R. Radhakrishnan, Chairman of S.I.W.S College. And finally, Professor Vikram Ethel, Department of Mathematics, to felicitate Professor Manali Londe, Principal of S.I.W.S N.R. Swamy College. To mark the auspicious beginning of our conference, we will now commence the ceremonial lamp lighting, a tradition that symbolizes the triumph of knowledge over ignorance and light over darkness. May I kindly request all our dignitaries on stage to participate in lighting the lamp. Thank you. Thank you, respected dignitaries, for gracing this occasion and lighting the path ahead for this enlightened journey. With this, we are ready to begin our inaugural ceremony. To formally welcome you all, I now invite Professor Ajit Kumar, convener of NCCGAML 2025 and head of the Department of Mathematics ICT Mumbai, to deliver the welcome address. Please welcome him with a warm round of applause.
A very good morning to all present. It's my great pleasure and deep sense of pride that I extend a warm welcome to each one of you on behalf of the Department of Mathematics, Institute of Chemical Technology, Mumbai, on the occasion of National Conference on Computational Geometry, Analysis, and Machine Learning. We are delighted to organize this event in collaboration with S.I.W.S College, Mumbai, reaffirming our commitment to fostering academic partnership and promoting interdisciplinary research. I'm especially honored to welcome our distinguished dignitaries, our Honorable Vice Chancellor, Professor A.B. Pandit, our chief guest of today's function, Professor Dipendra Prasad, who is also the chairman of the National Board for Higher Mathematics, president of S.I.W.S institutions, Sri R. Radhakrishnan, principal of S.I.W.S College, Professor Manali Londe, and keynote speaker of this event, Professor Anirban Chakraborty from Jawaharlal Nehru University, Delhi. I would like to take this opportunity to express my sincere gratitude and thanks to our Honorable Chancellor, Padma Bhushan Professor J.B. Joshi, and Honorable Vice Chancellor Professor A.B. Pandit for their unwavering support and invaluable guidance, which have played a pivotal role in making this conference a reality. I also extend my heartfelt appreciation to the leadership of S.I.W.S College for their enthusiastic participation and gracious collaboration. Actually, the concept of organizing this conference was initially proposed by Professor Hem Sundar, who is the head of the Department of Mathematics at S.I.W.S College, following which we had many rounds of discussions and with all the faculty members, and this current theme was selected. So our deep appreciation goes to all the faculty members of ICT Mathematics Department and also S.I.W.S College Department, whose tireless efforts and shared academic vision made this conference possible. I also extend special word of thanks to our students, volunteer and support staff whose enthusiasm and efficiency have greatly contributed in seamless organization of this event. The response of this conference has been truly overwhelming, with wide-ranging participation and high-quality submission from across the country. The broad interest, a clear indication of this growing significance of interdisciplinary approach that merge mathematical theory with machine learning and artificial intelligence. The conference theme seeks to explore the dynamic interface between classical mathematics and emerging computational methods and an intersection that is providing highly impactful in solving complex real-world problems across science and technology. We are privileged to host over 12 invited talks by eminent scholars in the fields of geometry, analysis, and topological data science, alongside several high-quality contributory talks and poster presentations. I'm deeply thankful to all the speakers and their valuable contributions. In fact, students and faculty members have also organized a brief cultural program this evening, so I invite you all to join us. One of the key highlights of this conference is going to be a panel discussion titled "The Role of Artificial Intelligence in Mathematics Education." As we all know, in this present increasingly technology-driven era, mathematics serves as a foundational pillar for artificial intelligence, while simultaneously gaining from AI powerful tools and techniques. This session will delve into the dynamic interplay between AI and mathematics and discuss how this relationship can reshape the landscape of mathematics education and enhance its significance in emerging fields. The panelist features distinguished group of experts drawn from both academia and industry. Beyond academics, our department takes pride in conducting numerous outreach programs for students and teachers across the country. Alongside our core teaching and research responsibility, these initiatives form a vital part of our mission. Our department offers distinctive and unique academic programs such as MS in Engineering Mathematics, a multidisciplinary minor degree in Machine Learning and Artificial Intelligence, which is open for all UG students, and a vibrant PhD program in mathematics. I warmly invite all of you to visit our website and explore these innovative and future-ready curriculums. Once again, I welcome all of you and wish you a stimulating and fruitful conference. Thank you all.
Thank you, Professor Ajit Kumar. Now I request our esteemed Vice Chancellor of ICT Mumbai, Professor Aniruddha B. Pandit, to deliver the inaugural address.
Today's chief guest, Professor Deepan, keynote speaker Anirban, Professor Radhakrishnan, Manali Donde, Ajit Kumar, my colleagues from mathematics as well as from physics, I can see some, and the student friends. I'm really feel very happy that this is a jointly organized symposium between S.I.W.S and ICT. My late father, our late wife, who retired from VJTI, Master of Computer Application Department, had a very close collaboration with S.I.W.S. Sudha Tumbe used to collaborate. But after that, I did not really keep in touch. But I'm really happy that we are reviving this. And I said other day, and I'm saying it and repeating it again. Mathematics is my favorite department in ICT. Simple reason is they don't come and ask for any money to buy an instrument, right? The only thing which they ask for, give me a latest computer or a workstation, and that is still much, much cheaper than any of these sophisticated analytical instruments. They don't ask for much space, though they always complain about the lack of space. We are going to create some. But coming back to today's topic, as correctly pointed out by Dr. Ajit Kumar, we are in a situation, I am saying situation or not, because even if you want to neglect AI, you cannot. And if you are not conversant with the techniques which are there available, whether it is ChatGPT or any other similar techniques, you will find it extremely difficult to decipher between what is copied and what is original. So students are, as always you know, are much more tech savvy than the faculty. Obviously, because of the age, they have grown up in that entire atmosphere as compared to what we were forced to learn, or similarly, now we are forced to learn about the AI techniques because students know much more than us. So a knowledge of AI, and since it is essentially a mathematical phenomena, because it derives completely on the basis of logic. And logic, if you express it in terms of equations, it becomes mathematics. So this logic, though we express it in terms of equations to start with, and as the logic becomes convoluted, complicated, mathematics also becomes that much more complicated. The situation here is such that mathematics is, as compared to all other sciences, is evolving at a much faster rate, but that dissemination of the evolved mathematics doesn't appear at the rate at which the technological or other science branches tend to publicize. You will see the publications occurring in the mathematical journals as compared to publications occurring in chemistry and publication occurring in physics. Even physics and mathematics both lag significantly as far as numbers are concerned. The simple reason is all these involve a thought experiment. And thought experiment is always very, very difficult to validate. And publishing paper without validation is always a bottleneck. And there is no journal available, or maybe one or two are just emerging, which is willing to accept a negative results. That means I tried a solution for this particular equation, I tried this technique, that technique, but did not get a solution. So don't waste time in following this particular technique. We are not allowed to publish it. And if you can't publish it, the one who starts solving and starts attempting to solve this equation goes through the same procedure and then realizes that somebody else has done it earlier, but he does not know that it has been done earlier. So it is necessary for us that whatever new techniques which are getting developed, it is mandatory for the teachers of mathematics to share it with the class as early as possible without waiting for them to publish in the papers and students learn after maybe 2 or 3 iterations and the reviews, processes, so on and so forth. So, mathematics teacher, he or she is continuously studying, continuously researching in his or her head. And as soon as he or she realizes that there appears light at the end of the tunnel, it is necessary for him or her to share it with the class, mainly because the class can significantly contribute and can be, as I have seen in the younger generation, much more innovative, but they need to be prompted. Whatever techniques which they have learned to study during their school days, they need to de-learn that particular technique because they rely mostly on rote learning, mugging without sometimes understanding what they are reading, what they are writing. The job for teachers is to make them think, and there is no better subject than mathematics for the students to make them think. Because without thinking, they can't remember the mathematics and then produce the answers to the equations. I used to have a mathematics teacher during my undergraduate days in BHU called R.N. Pandey. That fellow was absolute genius. He would walk up in the class with just a chalk in his hand and would dream up and come up with differential equations and the solutions, the methods to avoid that. And he had no end of such examples available. You go and talk to him anytime, you will find out something, he will derive something. Now, I have seen some people that they arrive at the conclusion without any formal training it, sheerly based on logic. And that is what is the ultimate goal of mathematician is. So I'm really very happy that you have chosen a topic which is extremely important and mandatory for all of us to learn. And geometrical patterns and machine learning are indeed the future of mathematics. What you can call as graph based solutions or graphical solutions, which chemical engineers are fairly familiar with, but they don't go beyond maybe a distillation column using a capital method or a similar design for extraction column. But here you have an opportunity that graph theoretical approach to come up with the solutions for extremely complex logic is the key, and AI and machine learning are going to definitely play a significant role in it. And as usual, I compliment the ICT mathematics department for taking up initiative, and I would like to thank S.I.W.S for joining hands with us and raising the level of this collaboration as well as the acceptance of today's seminar. Welcome to ICT. Enjoy the 2 days. Learn, have fun. Thank you.
Thank you very much, sir. We now invite Professor Manali Londe, Principal of S.I.W.S. N.R. Swamy College, to share her thoughts. Please welcome.
A very good morning to one and all. I extend my warm welcome to the Honorable Chief Guest, Professor Dipendra Prasad, Chairman NBHM. My sincere warm welcome to Anirab Chakrabarti from JNU, who is the eminent keynote speaker today. Thank you, Honorable Vice Chancellor, ICT, for giving us an opportunity to be the part of this august and scholarly gathering. Also, I am grateful to our chairman, Sir Radhakrishnan Sir, who is always there to motivate us for such kind of academic collaborations. I also extend my welcome to ICT Vice Chancellor himself, because he is the person who is a great source of motivation, I'm sure, for all the teachers and the students in ICT. the convener of this very conference, Professor Ajit Kumar sir, and my colleague, Dr. Hem Sundar sir. I feel blessed to share the dais with such an eminent or scholarly gathering and people here. Also the mathematicians sitting here of the dais. Personally, being the student of philosophy, I always feel and try to find the similarities between the mathematics and philosophy. And for me, when I tried to do research on this, the main parallels I found that the pursuit of knowledge and the importance of logic and critical thinking. Logic plays a very central role in both disciplines. Mathematicians use logic to construct proofs, while philosophers employ it to analyze arguments and evaluate claims. Both also require critical thinking to identify flaws in arguments, challenge assumptions, and develop well-supported conclusions. René Descartes, a great philosopher, eminent mathematician who was considered as the father of modern philosophy, he saw mathematics as a source of certainty and clarity, and he sought to apply its methods to other fields of knowledge, including science and philosophy. According to Descartes, mathematics was the only thing that is certain or true. He used to say, conquer yourself rather than conquering the world. René Descartes is the most commonly known for his philosophical dictum, as all of you know, that I think, therefore I am, and which was popularly known in Latin, cogito ergo sum. Descartes once said, quote unquote, human intelligence has a universal capability applicable to any surrounding situations, whereas machine intelligence is no more than a combination of abilities that are applicable only to certain situations that the creator could imagine when they built the automated machine. Descartes' argument was very clear. This point was rediscovered in 1960 and it continued till 1970s by computer scientists and philosophers, and it was given the name the frame problem. Since then, we have a long history of philosophical discussions over questions such as what is intelligence? What is required for a robot to become a truly intelligent being? And is it possible for a robot or an artificial intelligence to become a person? I feel this inquisitive attitude is the base for both the fields, the mathematics and philosophy. Today is the world of AI. Our day starts with AI, ends with AI. And I'm sure these 2 days conference or the deliberations for over the next 2 days will throw a light on this. And there is a lot to take home for all the participants. We are blessed to listen to the eminent speakers in this particular field. Machine learning, which is the subdivision of AI, I'm sure it's going to throw a light on the very, very relevant topic. I thank the organizers to have and selected this kind of a theme for this conference. I once again thank the ICT team to give us an opportunity in joining hands with them in organizing this academic venture. All the very best. I wish a grand success to this national conference. Thank you.
Thank you, Professor Lundi. I now invite Shri R. Radhakrishnan, Chairman of S.I.W.S. College, Mumbai, to deliver the presidential address.
Chief guest, Professor Dr. Deependra Prasad, Vice Chancellor of ICT, Professor Dr. Anirudh Pandit, Professor Dr. Anirban Chakraborty, Professor Dr. Ajit Kumar, our own Principal Dr. Manali, and our Professor Dr. M. Sundar, distinguished guests, esteemed speakers, delegates, and participants. Good morning, greetings to all. I had always wanted to be part of ICT because as a student of S.I.W.S, I used to walk from Matinga all the way to S.I.W.S school. So when I used to see this ICT, I used to think that I should be part of this institute. But it never happened, except that I am a chairman and we are neighbors today. And also Professor Sharma is a neighbor. I stay close to him. We both stay in the same colony. But I am today, it is my privilege and honor that I am here to address this intellectual elite gathering at the National Conference of Computational Geometry Analysis and Machine Learning. I welcome you all. I do not know this subject, I am not expertise, but I am here as a S.I.W.S chairman. And I always like to be a professor also, because I thought that teaching is a wonderful subject, because you connect with the entire mass, the future, and you always remain young. So whenever I am invited on such occasion, I try to ensure that I am on the stage, whether I am a professor or not. And I also have an advantage when I sit with this elite gathering like this with doctors. Generally, either they address me as doctor or they address me as professor. Like Mr. Pandit also said Professor Radhakrishnan. So I felt very happy. So whether I am not, but I get addressed that way. Today we have gathered here to explore the latest advancement and innovation in this interconnected fields, fostering a deep understanding of the complex relationship between geometry, analysis, and machine learning. As we begin this conference, we all recognize the pivotal role computational geometry plays in shaping our understanding of spatial relationship and structure. The integration of machine learning techniques with computational geometry and analysis has far-reaching implications across various disciplines. Father of computational science, Alan Turing once said, "We can only see short distance ahead, but we can see plenty there that needs to be done." This conference embodies the spirit of innovation and progress, and I am confident that the discussions and deliberation that will take place here will pave the way for new discoveries and breakthroughs. The synergy between computational geometry analysis and machine learning has numerous applications in fields such as material science, medical imaging, and data analysis. I don't have to say this before this big audience who are already aware about all this. As Stephen Hawking aptly said, the universe has no beginning and no end. Similarly, the possibility that arise from the intersection of these fields are endless. And I'm excited to see the new ideas and innovation that will emerge from this conference. I am sure this conference will provide a platform for experts to share knowledge, exchange ideas, collaborate on future projects, foster partnership, and contribute to the advancement of computational sciences. I extend my gratitude and thanks to the Institute of Chemical Technology, specifically Vice Chancellor Dr. Pandit and Dr. Ajit Kumar, for inviting the South Indian Welfare Society to partner and co-host this event. I also appreciate the efforts of the organizing committee, specifically our own Professor Dr. M. Sundar, reviewers, and all those involved in making this conference an exclusively unique event. I am confident my principal and team will have a lot of take home to offer to our students. As we embark on this intellectual journey, I am reminded of the words of the great mathematician Ida Lovelace. The more I study, the more insatiable do I feel my genius for it to be. Let us harness this insatiable curiosity and passion for learning to drive innovation and progress in the field of computational sciences. I wish all the best and hopeful that this conference will inspire meaningful interaction and fruitful conclusion. Thank you very much. Thanks so much.
Thank you so much, sir. We are deeply honored to welcome Professor Dipendra Prasad, Chairman of NBHM and Professor at IIT Bombay as our chief guest. A celebrated mathematician, Professor Prasad is renowned for his work in number theory, especially in automorphic representation and the Gann-Gross-Prasad conjecture. An alumnus of St. Xavier's College and IIT Kanpur, he earned his PhD from Harvard University. His accolades include the Shanti Swarup Bhatnagar Award, INSA Fellowship, and the Tuas Prize. We are privileged to have him with us today. I now invite Professor Prasad to address the gathering.
Thank you very much for all these kind words. I'm a mathematician, and I think it's a bit rare for me to give such chief guest talk. I guess I may have done it recently because for last 2 years I'm also the chairman of the National Board of Higher Mathematics, and I get the feeling that because of my new position, I am called upon to speak at more occasions, but still I'm not too comfortable in this role. I prefer to be a mathematician. So I will be quite brief. I'm very happy to see that Institute of Chemical Technology and S.I.W.S College have joined hands to bring this conference. The mere presence of the Vice Chancellor, Professor Aniruddha Pandit, and the principal and the chairman of S.I.W.S College means a lot to this conference, to indicate that they are supportive and they are happy to support mathematical activity. As a mathematician, I feel very happy that mathematics is gaining some popularity and support from various quarters, and I hope it continues. I know Institute of Chemical Technology has been very supportive of mathematics, and I have been now coming quite regularly here, and I have many good friends, and I feel that this institute has many excellent students, and by the presence of these colleagues in mathematics, I feel that the students will get a good opportunity to learn and to go on with their future careers around mathematics. I should just say a few words that for many students and their parents, a career in mathematics is a very uncertain career. But I feel that if you have some interest in mathematics and if you have some abilities, I get the feeling that it is one of the best career options these days, because mathematics itself has many options. But through mathematics, I think it also opens up the world of many possibilities, and all these newer possibilities which have arisen, artificial intelligence and machine learning, that seems to be the talk of the town, and any place I go to is always interested in hiring faculty who can teach the subject in mathematics. So I have the feeling that many students in undergraduate departments in mathematics are very keen to expand their knowledge of mathematics together with these subjects, and it appears to me that there is a world of possibilities in this country and all over the world. So I'm very happy that the topic for this conference is very topical. Artificial intelligence, also geometry, and I guess whatever we do these days has a relationship to these. So I look forward to this conference and happy to see the support the institutes of chemical technology and S.I.W.S college is giving to this. I hope for continued support and I hope to keep coming. Thank you.
Thank you, sir, for those inspiring words. To further enrich this academic event, we are honored to welcome Professor Anirban Chakraborty from Jawaharlal Nehru University, New Delhi, to deliver the keynote address titled Mathematics, Data Science and Complexity, Understanding Real-World Systems. A renowned physicist and complexity scientist, Professor Chakraborty holds a PhD from the Saha Institute of Nuclear Physics and an HDR from Université Pierre et Marie Curie, Paris. With over 2 decades of global academic experience, his pioneering research in econophysics, sociophysics, and complex systems has earned him the INSA Young Scientist Medal and was elected a Fellow of the TWAS UNESCO. Please join me in welcoming Professor Chakraborty.
Namaskar and good morning, everyone. Very thankful to the organizers, both ICT and S.I.W.S College, for inviting me to give this keynote address. And in presence of the audience, August gathering and a wonderful audience, I'll try to keep it as short as possible and as non-technical as possible. So you'll see that there are 4 cartoons of examples of what we call complex systems. One is of the stock market. The second is a flock of birds, and there are 70,000 starlings making ordered and disordered motion. The third is about a traffic system, which again is sometimes order and sometimes disorder, which leads to a jam. And the fourth one is a sort of Arctic sea ice expands, which is an example of an environmental system. So I've been working for more than 2.5 decades on these type of work, and these are my collaborators. I could not place all the collaborators in one slide, so I apologize. Dr. Shorish is here. He has been collaborating with me for the last 10 years. And then I have many collaborators across the world and my PhD and postdoc students. You'll see that I've been hopping across the globe. So I finished my PhD from Shah Institute. And then I was a postdoc at Helsinki University of Technology, which is now known as Aalto University. And then I went to Brookhaven National Lab, which is very famous for particle physics. And then I came to Benares Hindu University as a lecturer in theoretical physics. After that, I was offered a position in the chair of quantitative finance by BNP Paribas at École Centrale Paris. And then JNU offered me to come and start this field of complex systems. And in 2014, I joined JNU. For a brief 2 years, I had taken leave from JNU and gone to BML Munjal University, which is under the Hero Group, to start the School of Liberal Studies and also as Dean of Research and Dean of School of Engineering. So this is a top view of JNU, which is a very green campus in the heart of Delhi. And those are my PhD scholars and then some master students whose work I will be presenting. As all Bengalis, I'm always inspired by Kavi Guru Rabindranath Tagore. And you'll see that one of his quotes on education was that the highest education is that which does not merely give us information, but makes our life in harmony with all existence. And we'll see that sustainability is one key word which he has been propagating. Those who have been to Shantiniketan would see that the departments which he had established have no doors and windows, because he didn't want knowledge to be constrained in a closed space. And he was way ahead of time that when he established Vishwabharat University in the 1925. He talked about sustainability, entrepreneurial activities, and many other concepts. Inspired by him, we also had a startup which is called H2 Solutions, E equal to H2, the Planck's formula, and where we, work with reusage and recycling of lithium-ion batteries and converting IC engines to electrical engines. I'm also a founding member of Center for Complexity Economics, Applied Spirituality, and Public Policy in general. Now, if you're wondering what applied spirituality has to do with science, the next quote will tell you. This is a famous quote by James Gustav Speth, from a US advisor to climate change, and he was the head of the UNDP. I used to think that top environmental problems were biodiversity loss, ecosystem collapse, and climate change. I thought that 30 years of good science could address these problems. I was wrong. The top environmental problems are selfishness, greed, and apathy. And to deal with these, we need a cultural and spiritual transformation, and we scientists don't know how to do that. So you'll see that if you want to solve problems like climate change, you'll see that none of the protocols in Kyoto, Paris, they are working because the rich nations, the developed nations are greedy and they are selfish. And we have to think beyond us and ourselves. Unless we do that, we will not be able to solve these problems. Coming to complexity science, I wanted to first start with what is science. Now, science is, of course, a knowledge or a system of knowledge covering general truths or the operation of general laws, especially as obtained and tested through scientific method. Now, what is a scientific method? So I have a cartoon which shows that a child discovers an object and makes a hypothesis that it's an edible object. So it does the experiment, takes the object, puts it in the mouth, and then it analyzes the data, which shows that probably it is not an edible object. So it starts crying and reports its findings, and then it invites other kids to come and reproduce. So these two things are very important in science. One is verifiability, and the second is reproducibility. And often when we are in a dilemma, what is science and what is pseudoscience, this criteria would help you to, distinguish what is pseudoscience. Now, typically, the way we do science is what we call a picture of reductionism. As René Descartes, which Manon mentioned, he was one to start that you can reduce a complex systems to simpler objects. And so if I ask you the question, what are we made up of? You will probably say that we are made up of tissues, the skin, the blood, the bone, these are all tissues. What are the tissues made up of? Cells. What are cells made up of? Different organelles like chromosome, ribosome, mitochondria. What is the chromosome made up of? DNA. What is the DNA made up of? Chemical atoms and molecules. What are the atoms made up of? They're made up of electrons, neutrons, and protons. What are the neutrons and protons made up of? They are made up of quarks bound by gluons, as by your particle physicist friend will tell. And then if I ask what are the quarks made up of, there are string theorists who would tell that they are made up of strings, and what we see are actually the different vibrations of open and closed strings. Now, this is a picture of reductionism. So you will think probably that the sciences are arranged in a hierarchical order. But you'll see that there was a wonderful article written by Phil W. Anderson, a Nobel Prize winner in physics, who wrote the article More is Different way back in 1972, where he said that if I know particle physics, there is no guarantee that I understand chemistry. If I understand chemistry, no guarantee I understand biology, because at every stage, there are new laws, new concepts. And so we often have to come up with an alternate approach, which is the integrative or complexity approach. So this is a cartoon which is telling the same thing, how pure the fields are. And so psychologists teach the sociologists that it is applied psychology. And biology tells psychology is applied thing, and it goes on. And then we have the mathematicians. They said, oh, I didn't see all. We are the most pure subjects. So what is mathematics? As Galileo put, mathematics is the language with which God has written the universe. Now, of course, he meant it as a metaphor because he says that mathematics allows us to make quantitative measurements, formulate relationships between quantities, and make predictions. And later, you'll see that Professor Richard Feynman, who's again one of the most popular physicists and a Nobel Prize winner, resonated the same thoughts. Mathematics is not a language, but it is language plus reasoning. It's a language plus logic. Mathematics is a tool for reasoning. It's in fact a big collection of results of some personal, careful thought and reasoning. By mathematics, it is possible to connect one statement to another. So that, as I'm trained as a physicist, I think in the same way, and we'll see how we apply these things in solving some of these problems. So as I told, complexity science is a new field of science where we work with multiple constituents of the system which interact with one another and gives a collective behavior where we see nonlinear dynamics, emergent behavior, spontaneous ordering, and many things. So you see the example of a Lorentz attractor or a stock market. These are some of the examples of the complex systems. If you want to know more, you could see an issue of 20 articles published in Science in 1999, which deals only with complex systems. And if you go to Wikipedia, you'll see that there are different tools that are used to study complex systems. In my own research, I have been using these fields encircled in red. I started with collective behavior in physics, moved to game theory, which is at the interface of maths and economics, then to nonlinear dynamics, network science, pattern formation, and evolution and adaptation. So here I show, for example, the simplest chaotic mechanistic system which displays chaos, which is a double pendulum. And I think almost all of you have solved this in class 12 or in the first year of your undergraduate degree. Now, if I have 2,500 such pendulum, and I'll play a video which will show you that sometimes, even though they are not coupled to each other, but you will see that there is chaos and there is ordering. And this type of things have helped people to understand complex systems. If you are interested, there's a wonderful book by Professor Dwight Farmer, who's now at the Institute of New Economic Thinking in Oxford. But he was a nonlinear dynamics and chaos expert in Los Alamos. He's written a wonderful book called Making Sense of Chaos. Now, in 21, the Nobel Prize in Physics was given to complex systems, especially Giorgio Parisi, who was working with disordered systems. He was the one to model these movements of flocks of birds. So he wrote a book called In a Flight of Starlings. And there, the review, they said that, okay, just the way the molecules of water are bound together by electrical forces, so as all the avian instincts steer them into ordered and disordered motion. Now, last year, when the Nobel Prize was given to Hinton and Hoffield, there was a lot of criticism in physics because they thought that this is not physics. And then there was a wonderful article published in Nature where they interviewed Professor Hoffield. And then he said that physics is not what you are working on, but how you are working on it. So if you have the attitude of physics, then what you're doing is physics. Now, when I started my PhD in econ of physics, I was one of the first ones in India and across the world. I used to get criticized similarly. When I used to talk to physicists, they would say, oh, you're doing economics. And when I used to talk to economics, they would say, oh, you're doing physics. So it's not an easy thing to do. Now you'll see that there is a deep connection between statistical physics or mechanics and neural networks. I won't go into the details. And then the next day, again, the Nobel Prize in Chemistry came from AI and machine learning, where they used machine learning to classify different types of proteins using the AlphaFold 2. So there was a wonderful article in New York Times which said that, out of these 5 people who are given Nobel Prize, only one is a biochemist. The rest are not from the parent fields at all. And then they wrote actually that when Nobel started the prize in 1895, he thought that there would be lone genius working in physics or in chemistry or in medicine. But nowadays we have everything with interdisciplinary applications. And so you'll have subjects like geochemists or paleontologists or computational evolutionary theorists or astrobiologists. And so you'll see that now we're working on problems which cut across disciplines. And so AI is the latest part, and we are alarming because the way we use AI will depend on us. So if we use it responsibly, it will be our benefit. If we abuse it, it will go to our disadvantage. Now, what we were talking is basically reflected in this Buddhist parable, which talks about 6 blindfolded men touching different parts of the elephant and thinking that they are different objects. So often when we do science in silo, we are like this blindfolded men. What we need to do is actually take off the blindfold, and then we'll see that we're working on a larger problem. So we need a holistic and interdisciplinary approach. And when Stephen Hawking was asked that, what advice do you have for the young graduates? He said that 21st century is going to be the century for complexity. And two skills which people need to pick up, especially the undergraduates, is statistics and data visualization. Now, I'm reminded of another Nobel laureate in economics, Herbert Simon, who was first one to apply AI in economics. And he said, perhaps the right way to move is to understand before one predicts. Because often the computer scientists are interested in prediction, but as natural scientists, we are interested in understanding the system. So with that, we started bridging the data and science, and we came up with a book called Data Science for Complex Systems, which I've written with economists and statisticians, and I'm a physicist myself. So how do I apply this data science, which is an interdisciplinary field based on maths, statistics, and computer programming? So you'll see that prediction of markets started way back in 1910, 1913. These were the first two articles which talked about prediction and forecasting of price. And even after 100 years, when 2008, we had the subprime crisis or the dot-com bubble, or what happened just a few days ago when DeepSeek came and $600 billion was wiped out for the NVIDIA. Now, these events in markets are difficult to forecast. However, markets are very interesting systems which act as model complex systems because there are agents who try to find the best price. So they trade the stocks, either buying or selling, and they try to find the prices. And what we see are the price movements, and then we try to examine them using data science. So typically what we do is we look at the closed prices, compute the returns, and then, for example, we look at the correlations or co-movements of prices. And here I have an example of 194 stocks across 32 years from 1985 to 2017 of New York Stock Exchange. And you will see that the correlation matrices change with time and display very interesting patterns. And there are particularly patterns when they are very correlated, and that those correspond exactly to the crashes. So the Lehman Brothers crash in 2008 or the Black Monday crash in 2007, these were some of the biggest market crashes. These are also periods when we have a lot of uncertainty, and you'll see the risk and the volatility of the markets go up. Now, these are states which we in physics we call critical states. And there was a wonderful article written by Martin Scheffer, which talks that across complex systems, not only finance, but in ecology, in environment, you'll see such type of things that during the critical period, the thing becomes extremely stressed and it becomes homogeneous and very well connected. And at normal periods, they are heterogeneous and you will not see so much stress building. So we used a lot of analogies between, for example, earthquakes and financial markets, and use the same types of tools and techniques to study the behavior of markets. So in my own research, I have been doing for the last many years. We have several papers, and I'll just give you a glimpse in the last 2-3 minutes about what we are doing. So what we try to do is look at these patterns of correlations and then try to compute a L1 norm distance. And then we find that the market behaves very differently. And those are the 3 times which we have bubbles and crashes. So we can use such techniques to identify when the market is behaving abnormally. And then we try to understand through machine learning that there are different types of states in markets. And these states, if you take randomly, would belong to these 4 states. And you can construct when the period of market was in what state. And then you can compute what we call the transition probability. So if I know that I'm in state 3, then there is a high chance of a market crash coming. Now that information alone can help you to strategize and win a lot of money in the stock market. Similarly, all of you are familiar with the PVT diagram, which gives you the phase diagram of water. We wanted to construct such a phase diagram for the financial market. So what we did is started with the returns, made correlations, and decomposed them into different modes. And then we constructed the entropy function, which tries to characterize the structure of the correlation matrices. And then we found that there is a very interesting behavior that whenever this is a I think a video which may not be working so well. Anyway, it shows that you can divide the market into different phases, and in the normal period it is gray. When it goes to the crash, it goes to the red one, then it goes to the green ones and comes back. Whereas whenever we have bubbles, it goes to the blue ones, then the deep blue ones, and then comes back to the base. So whenever we have events like this, we can actually track them. And then we found that this is not only true for the US market, but also true for the Japanese market. And now my student in masters is actually working only with the tech stocks to see what we had in the .com bubble and what we are now having in the AI bubble, how similar they are. So in one hand, we find that they are similar, which is shown in the bottom right. And on the top, they're showing that no, those two bubbles also are different. So the .com bubble is different from the AI bubble. Now it is our duty to understand and probably predict when will be the crash after this. Now, discrete geometry studies, we have applied tools of discrete geometry like Ricci-Forman curvature and applied to stock markets. I won't go in the details, but again, we construct networks and then we compute this discrete geometry curvature methods on the networks. And they will show you that when the markets are undergoing transitions. Right? So we found that bubbles are more difficult to identify, but these type of tools from discrete geometry help us to identify the bubbles more easily. Similarly, we are using topological data analysis, and I know that Priyavrata and also Michael will talk in the afternoon session on persistent homology and topological machine learning. So I won't go through the details, I'll just skip the slides. For those who do not come from topology, you understand we tease the topologists that they cannot distinguish between a cup of coffee and a donut, or a cow and a sphere, because you can make with continuous transformations one move to the other shape. But we are using these concepts of simple shell complexes and persistent homology to look at how the bar diagrams and persistent homology diagrams would look like. So for different stages of those correlation matrices, we put them as the data points, and then we find that they also can give you a very good idea of what is happening in the market. And using that, we looked at the Indian stock market, especially in the last 2 decades. And we found, again, that you can talk about all the crises and the bubbles and crashes. So moving, I don't think I have much time, so I'll go very quickly. We are applying also tools of machine learning to solving problems of farmers. This work I'm doing with Shourish actually, where we take the price of crops like soybean or brinjal, and then we help to understand how the volatility would look like and use machine learning to predict what the volatility would do, because that will help the farmers to allocate their resources of land. Similarly, what we are doing is working on the minimum support price. This is an ongoing work with Shourish, and we are saying that depending on the climate scenarios that we will be having in the next 80 years, we'll be able to predict how the MSP should be better formulated. And last few slides on very important problems, especially where I come from, Delhi, it's a havoc, the pollution. And we are working on studying the causal links between anthropogenic emissions and air pollution dynamics. So we are taking the data, the time series, and trying to look at how the PM 2.5 and the ozone are working. And using the machine learning models, which are given here, we are trying to understand how the behavior is in the Delhi NCR. So you will see that the PM 2.5 and ozone are negatively correlated during the day, but positively correlated during the night. And so if you want to control, it is very difficult to devise a single strategy. Similarly, we are trying to look at heat waves and the mortality in India and trying to predict how things would go in places like Delhi, where temperatures start ticking at 48 degrees in the summer. Or we are looking at the climate change vulnerability of different states. And here we were seeing that we can project the current vulnerability and what will happen in 2085. So using models of machine learning and data science, we are trying to understand how things will go. So you'll find a wonderful article in Nature Communications that tells that these systems are not so easy to study because they have lots of feedbacks. And how AI will influence is difficult because some of the goals of SDGs, there will be a positive impact, but in other places it will also have a negative impact. But definitely artificial intelligence, machine learning and all are helping us to improve our climate models and trying to do this type of thing. The last takeaway message is, I haven't talked the physics behind it, but whatever we study in spin glass is also the one which was extended to neural networks, is similar to what is found in portfolio optimization and also in studying economic complexity. Now that's the maths and the physics part which I've skipped in the keynote address because of paucity of time. My papers you can find in the Google Scholar, and I have written several books. 3 of them are from Cambridge and 1 in Wiley. And I've edited a whole lot of books. So those who are interested, if you write to me, I can share all of these. And with all my hard work of my collaborators and students, I was elected as the S.I.W.S fellow, and in the field of economics and social sciences, which was a recognition of my work as a physicist to economics. And this is my homepage and email ID. Thank you for attention.
Thank you, Professor Chakraborty, for the brilliant address and the talk. To formally conclude this inaugural ceremony, I now have the privilege of inviting Professor G.B.V. Hemasundar, co-convener of NCCGAML 2025 and head of the Department of Mathematics at S.I.W.S College, to deliver the vote of thanks.
Good morning to one and all present here. I hope you all enjoyed the morning inaugural session of the National Conference on Computational Geometry, Analysis and Machine Learning. Thank you all for taking the time to join us. Our presence here is a testament to the importance and relevance of the theme of the conference. I am Professor Hemasundar Balakota, co-convener of the conference, and I take this opportunity to deliver the formal vote of thanks. I express my deep gratitude to our chief guest, Professor Dipendra Prasad, an eminent mathematician and chairman of NBHM, for graciously accepting our invitation and honoring this inaugural session with his presence. Also, I sincerely thank our keynote speaker, Professor Anirban Chakravarti from JNU Delhi, for sharing his valuable insights and expertise. My heartfelt appreciation goes to the Honorable Chancellor of ICT, Padma Bhushan, Professor J.B. Joshi, whose unwavering support made it possible to host this conference at ICT, Mumbai. I also thank the Honorable Vice Chancellor, Professor Aniruddha B. Pandit, for his continuous encouragement and for joining us on this special occasion. I am grateful to Sri R. Radhakrishnan, Chairman of S.I.W.S Institution, for his gracious presence and generous support as one of the sponsors of this conference. And a special thanks to Professor Manali Londe, Principal of S.I.W.S College, for her enthusiastic encouragement towards this collaboration and for attending today's inaugural session. I thank the scientific committee and local organizing committee for their efforts and arrangements for the conference. I sincerely acknowledge our sponsors, ANRF, DST, Government of India, JP Joshi Research Foundation, Fine Organics, and our host institutions, ICT Mumbai and S.I.W.S College, for their valuable support. I must mention that the initial idea, of course, Professor Ajit Kumar pointed out, for this conference took shape during a meeting with Professor Ajit Kumar, convener of this conference at ICT. I thank him and the faculty of the Department of Mathematics ICT for their tireless efforts. My appreciation also goes to the mathematics faculty at S.I.W.S College for their valuable contributions. I would like to thank the technical and non-technical staff, along with the student volunteers of ICT Mumbai, whose dedication ensured the smooth conduct of today's session. Last but not the least, I extend my heartfelt thanks to the participants who have traveled from across the country to attend this conference, to share their work and engage with the academic community. Thank you once again to everyone present here. Thank you.
Thank you, Professor Hemasundar. I request all the dignitaries and participants to kindly proceed to the Marble Hall for a group photograph followed by high tea. We will reassemble here at sharp 11:10 a.m. for the first technical session on mathematical analysis. Thank you all once again, and let's look forward to 2 inspiring days of learning, sharing, and collaboration.
Yeah.
So marvelous.
Yeah.
So Kamalesh must have been there with you doing this.
Yeah, he was
He's
there.
friend.
Palash Pal.
Kalash is referred couple of people. Because I worked only on YouTube ones.
Very nice. Yeah, no, I'm very happy. Picture. Marble.
कार में रखना उनका भी ले लीजिए
चलो चलो फोटो खिंचाने का नहीं दादा
वो कार है नेक्स्ट सेक्शन और 2 मूवमेंट लगेंगे अच्छा 1C के लिए 3 लगेंगे ना वो इधर ही
इसका बात है कितना है
दो एक्स्ट्रा अभी जाके रखो
हाँ ये स्लोप है ना ऐसा, तो इसलिए सर ऐसे खड़े थे। कौन क्यों नहीं, फोटो अपन बाद में लेते हैं।
हाँ तो वो वाला माइक रख लेना।
कनेक्ट वही
है ना?
करेगा। हाँ ये रहा।
हाँ चार्ज चेक कर।
चार्ज चेक किया सुपर।
लैपटॉप सामने लगा देते लैपटॉप लगा देते सामने
हाँ वही इधर रख रहे हैं सर, और उनका माइक आउटपुट नहीं आ रहा करना। वो ये स्लिपरी है ना, इसका चेक करो, इसका माइक चेक करो, बैटरी तो है ना इसमें। इसका ये कहाँ गया स्पंज? हेलो कैसे रहता है?
ऐसे ही है, यहाँ से कहाँ से तो है ना। तो बंद करना
यहाँ पे लगा।
आप तो लगा
ये मुझे स्क्रीन चेंज करना है।
प्रेशर लगाओ।
कॉलर साइड लगा बाजू में।
हेलो
वो टाइट होगा वैसे लगाएंगे तो, उनको नीचे ऐसे ही लगाना होगा।
सही लगा।
ऐसे लगाना
और हर टॉप के बाद मोमेंट लेके
जॉब
वो आएगा।
लैपटॉप को बड़ा वाला ये है क्या कार्ड रीडर का?
उसका लैपटॉप में होगा मोस्टली, उसका ये
नहीं है
ये
उसका।
नहीं है।
किधर गया? मेरे पास वैसे मेरे पास कैसे है ये उधर साइड में रख के चालू रहेगा अरे इधर अवेलेबल हुए अरे वो अभी देख रहा हूँ मैं अभी जाने नहीं दिया सुबह आए इधर लाल लाल हो गए इसीलिए तो कस्टमर नहीं ना ऐसा चालू करा दो ए slide no second law. I think today morning I sent one.
Yeah, I updated.
You updated that. If I see the file name, I will know that this is mine.
This is great.
Oh, it just says updated.
This one.
should be.
Should I?
You have updated today morning. No?
Yeah. That is this one.
From the beginning, from that I cannot figure out. Something inside I have changed.
If you know the page number.
Skip scrolling and just do maybe something I can scroll. At least there is an example. Just want there will be some examples written at the top. So that definitely will pass it over this. Okay. Fine. Example. Puja.
This is it,
Fine,
right?
yeah. That example I thought was good for the
मूवेबल आहे तर त्याची वायर जोडलेली ना तुम्हाला कशी अरेंजमेंट लागली
Everyone, please settle down. We'll be starting in a minute.
Yes. If you want to sit down. Not comfortable.
Yes.
Good morning once again. We now begin the first technical session of the day, session 1A on mathematical analysis. This session will feature a series of invited talks by distinguished speakers from leading institute. It is my pleasure to invite the session chair, Dr. Akshay S. Rane from the Department of Mathematics, ICT Mumbai, to take over and conduct the session. Over to you, sir.
Thank you, Gopal, and welcome back after the tea session. And it gives me immense pleasure to introduce Professor Sudhir Kulkarni. Needless to say, the distinguished mathematician, and his area of expertise is functional analysis. And he has been a professor at Indian Institute of Technology, Madras, and later he went to IIT Palakkad and Dharwad. And in general, we know that computing spectrum of operators over real vector spaces is a daunting task. And his work has been extensively in real Banach algebras. And I welcome him to deliver the talk on the nullity theorem, its generalization and applications. Thank you, sir. Yeah, half an hour. So it is till 11:45. 11:45, half an hour. So this is 11:30 in this, so 12. 12.
Okay,
12 with that.
Thank you, Dr. Akshay, for such a nice introduction. And I also thank the organizers, namely Department of Mathematics at ICT and also S.I.W.S College. As you can see from the title, the purpose of this talk is to introduce about this nullity theorem. It's a theorem which is quite interesting, but somehow not so well known. In fact, I myself did not know it for quite some time, and I came to know about it when I listened to a lecture by Dr. Ravindra Bapat from ISI Delhi Center. So in this talk, I will try to introduce that theorem, and as the title says, some generalizations and some applications. So before going to the statement of the theorem itself, I will just talk of one particular consequence. It was quite interesting. I think all of you have what is meant by tri-diagonal matrix. Tri-diagonal matrix is the matrix where non-zero entries can come only on the main diagonal, and one diagonal above, which is called super diagonal, and one diagonal below, which is called sub diagonal. And in every other place, the entry must be zero. So such a matrix is described completely by 3n minus 2 numbers. That is n numbers coming on the main diagonal and n minus 1 numbers coming on the other two diagonals. So if you take the sum, it is 3n minus 2. So normally what we can think is that whatever you want to say about that matrix, we should be able to express in terms of this 3n minus 2 parameters. Okay? That's the general thinking. Now it is known that if a tri-diagonal matrix is invertible, its inverse need not be tri-diagonal, except when it is diagonal, inverse is also diagonal, but in general, for other tri-diagonal matrices, inverse need not be tri-diagonal. But we may still expect that each entry of this inverse we should be able to express in terms of these 3n minus 2 parameters. And that is indeed true. And that leads to one very interesting observation. It is known that the tridiagonal matrix is of order n, then every submatrix of A inverse that lies on or above the main diagonal is of rank less than or equal to 1. Similarly, every submatrix that lies on or below the main diagonal is of rank less than or equal to 1. Of course, the whole matrix is not of rank less than or equal to 1. It's an invertible matrix, so its rank has to be n. But this is about the submatrices. Okay? Now, several proofs of these results are available in the literature, and this paper which I mentioned, Wilbur-Strong and interplay of ranks, etc. By the way, this Wilbur-Strong is very famous. This book on linear algebra is quite well known and used practically everywhere. In view of this result, inverse can be described using 3n minus 2 parameters as follows. Okay? To start with, we can choose 4 n numbers. Let's call them Aj, Bj, Cj, Vj, etc. from 1 to n. The ith entry of A inverse can be described as Ai into Bj for I less than or equal to j, and Ci into Bj for j less than or equal to 1. And moreover, these 4 n numbers have to be also connected using the following relations, because on the diagonal, both these things have to coincide. So Ai and Bi has to be Ci for I equal to 1 to n. And then for one, see the whole idea here is that since the rank is less than or equal to 1, every entry coming in all other rows is just a multiple of one particular row or one particular column. So whichever row it is, for that particular row or column, the multiple is 1. So A1 and B1, A1 and C1 are 1. Now, one proof of this theorem depends on what is called nullity theorem. This uses the idea of what are called complementary submatrices. Let me just introduce what is meant by complementary submatrices. Let A and B be square matrices of order n. Suppose M is a submatrix of A and N is a submatrix of B. We say that M and N are complementary if row numbers not used in one or the column numbers used in the other. May appear a little bit complicated to begin with, but anyway, after you get used to it, it will be very easy. More precisely, we can describe it as follows. Suppose you use I and J as indexing sets, that is subsets of the numbers 1 to n, and let us say I complement for complement of I. Then Aij denotes the submatrix of A obtained by choosing the rows from I and columns from J. And similarly, then Aij and Bj complement A complement are complementary submatrices. That is, if you choose submatrix choosing rows from I and columns from J from A, and if you choose submatrix choosing rows from J complement and columns from I complement in B, then these two submatrices are called complementary submatrices. Now, with this terminology, the Learning theorem can become a very simple statement. It simply says the following: complementary submatrices of a square matrix and its inverse have the same nullity. That is, you take square matrix and its inverse, and you choose one submatrix here and its complementary submatrix in A inverse, then these two submatrices have the same nullity. That is nullity. And this has very interesting consequences, including one of the theorems which I mentioned earlier about the tridiagonal matrices. Okay, let me just give a illustration. Suppose you take a square matrix of order n and you choose some number k less than n, strictly less than n, and divide partition the submatrix as follows. That is AK, BK. That is AK is the consists of first k rows and first k columns, and rendering matrices accordingly. So suppose you do that, and suppose we take its inverse, and suppose, oh sorry, it is not A, it is N, sorry, it is a matrix M, and suppose we take M inverse, and then divide the M partition, M inverse also in the same fashion, PK, QK, RK, SK, etc. That is, PK is first K row and first K columns. Then nullity theorem says that nullity of AK is same as nullity of SK, nullity of DK is same as, etc. That is, those equations are given. What you will note is that AK was the submatrix lying in the top left corner for A, and its nullity is same as the nullity of SK. And similarly, you can see the other things. So, as I said, Gilbert Strong and his co-author have given a proof of this theorem and discussed its consequences for ranks of some submatrices. In particular, they do a very interesting fact that submatrices of a banded invertible matrix lying above or below the main diagonal have low ranks. One illustration is what I call tridiagonal matrix. That is one instances of what are called band matrices. So they mentioned in that paper that a very key question will be the generalization to infinite dimensions. That is what I'll talk about in the subsequent part of my lecture. Now, to talk of infinite dimensions, we take arbitrary vector spaces x and y, and we give some notations. Let L x y denote algebraic set of one linear operators from x to y, and for an operator T in L x y, this null space of T denotes the algebraic set of all x for which k is equal to 0, and range of T, the range of x, T, etc. And we'll Lxx P shall be denoted by Lx, and a map P in Lx is called a projection P spherical. Now, these are all standard definitions. Let P be a projection in X and Q in Y, that is Q in L and Q in L. Then the restriction of QTP to the range of P can be viewed as a linear operator from range of P to range of Q. Then again, look at this carefully. QTP. So it will be if you take any x in the range of P, Px will be simply x, then it goes to Px, and Q will take it to the range of P. So it will be a map from, we can view it as a map from range of P to range of Q. So it is, so we shall denote this as a T subscript P comma Q. It is, it's a section of T by P and Q denoted by T subscript P and Q. It is called a finite section if range of P and range of Q are finite dimensional. When T is invertible, the section T inverse, that is I y minus, that is identity of y minus 2 and identity of x minus P of T inverse is called the complementary subset. Remember that when P is a projection, I minus P is also a projection, and similarly for Q. So if you take the projections I y minus 2 and I x minus P and take the corresponding section, then that is called the complementary section of T. With this terminology, our null space theorem, which instead of calling nullity theorem, now I call it null space theorem, which is generalization, can be stated in the following very simple form. The null space theorem, let x and y be vector spaces, and let P in Lx and Q in Ly projections, and T invertible transformation. Then there is a linear bisection between the null space of T suffix Pq of T and the null space of its complementary section T inverse suffix I y minus 2 I x minus P of T inverse. And this is published in the paper which I mentioned there. And in particular, if this null space of P is finite dimensional, then since there is a linear bisection, their dimension will be the same as same, nullity is the same. I will speak the proof. Okay, the Strong and his co-author have discussed several applications of the nullity theorem. And what happens is that proof of these applications also involve the famous rank nullity theorem, which is also called sometimes fundamental theorem of linear algebra, especially by Hilbert's time. Now, we don't have such a theorem available for infinite dimensional spaces. So we have to have a different approach. So let us see how we can go about infinite matrices. Now, when it comes to infinite matrices, what happens is that we have to deal with the infinite sum. So we naturally the questions of convergence etc. come into picture. So we have to go to instead of linear algebra, we have to go to functional analysis. So talk of infinite matrices. So consider Banach space X with a Schauder basis A1, A2, etc. And we'll say that a matrix is with respect to that Schauder basis. And this is the theorem. Let X be a Banach space with a Schauder basis A, which is A1, A2, etc. And let T be a bounded the same as continuous linear operator on X. Suppose the matrix of T with respect to A is tridiagonal. If T is invertible, then every submatrix of the matrix of T inverse with respect to A that lies on or above the Venn diagonal or on or above the Venn or below the Venn diagonal is of rank less than or equal to 1. And I like to give the idea of the proof of this theorem because I like the statement of Paul Holocaust that every lecture should contain at least one small proof. So this let's see, if we can't compute, I'll give the proof. So now suppose M will be the inverse of T with respect to A. Then M is infinite matrix of the form. It's a tridiagonal matrix. So let us say entries on the diagonal are delta 1, delta 2, etc. And entries on the super diagonal alpha 1, alpha 2, etc. And entries below in the sub diagonal beta 1, beta 2, etc. And then the matrix of T inverse with respect to A is M inverse. Now let us fix some notations before going to the proof. Suppose M inverse I z entries gamma I z. And let Cz denote the Z column of M inverse and Ra denote the ith row of M inverse. So then the matrix M in the terms of the columns will be C1, C2, etc. And in terms of the rows it will be R1, R2. Further, what we do is that for a fixed natural number k, let C subscript j superscript k denote the column vector obtained by deleting the first k minus 1 rows, first k minus entries from C. That means you omit gamma 1 j, gamma 2 j, up to gamma k minus 1 j, and then start from this gamma k j, gamma k plus 1 j. Similarly for Rik. Now let Pk denote the submatrix of M inverse given by Pk equal to gamma Ij for I bigger than or equal to k and 1 less than or equal to z less than or equal to k. That is C1k, C2k, etc. Let me express it in words. What it means is that you take the first k columns and omit the first k minus 1 rows. That is submatrix that you obtain there. That is Pk. And in a similar way, do something similar for rows, you call such a matrix as Q. Now, what is to be observed here is that every submatrix of M inverse that lies on or below the main diagonal is also a submatrix of this Q. And similarly, every submatrix that lies on or above the main diagonal is a submatrix of Pk for sub. So if we show that each of these Pk and Qk are of rank less than or equal to 1, we are done. So let us try to do it. So it is sufficient. This is what I said right now. It is sufficient for to show that Pk and Qk are of rank less than or equal to 1. It is obvious for k equal to 1 because equal consists only one column or one. So just look at k equal to 2. Now consider the equation M inverse M equal to I. And let us write the full form. Write M inverse in terms of column C1, C2, etc. and write this matrix in the full form. Now, what we want to do next is that compare the first columns of both sides. Compare the first columns of both sides. So, if you multiply out in the left side, the first column will be delta 1 C1 plus beta 2 C. All other entries are 0. And that is equal to E1. That is equal to E1. First column delta 1 C1 plus beta 2 that is equal to E1. Now, E1 is a non-zero vector. So, delta 1 and beta 2 both cannot be 0. Alright. Now, what you do is that remove the first row from all edges. Then the right hand side becomes what we have called E11 or E12. But Even is the vector which is 1, 0, 0. So when the first entry is removed, it simply becomes 0. It simply becomes 0. So this equation now becomes delta 1 C12 plus beta 2 C22 is equal to E12, that is 0. But this means that C12, C22 are linearly dependent because we have observed already that at least one of delta 1 and beta 2 is non-zero. Which is same as saying that you look at this matrix P2, C12, C22, that is of rank less than or equal to 1. So what we are done for k equal to 2, with little bit more work, we can do a similar thing for k equal to 3. I'll just do that. Next, we compare the second column. Second column will be alpha 1 C1 plus delta 2 C2 plus beta 3 C2, that is E2. Now what is E2? E2 is the vector 0, 1, 0, 0, 0, etc. So now what we do is remove the first two entries from all, first two rows from all. Okay. Then what we get is alpha 1 C12 plus delta 2, alpha 1 C13 plus delta 2 C23 plus beta 2 C23 C23 is 0. Which again means that these three vectors C13 are linearly dependent. But we already know that first two are already, see, they are the sub columns of the two columns which are already linearly dependent. So one of them is a multiple of the other. And then the third one is also dependent on them. So if you form the matrix consisting of all these three columns, it has to be of rank less than or equal to 1. And now I think you get the idea. If you take the matrix P3, C3, 2, etc., it's linearly dependent. It's a matrix of rank less than or equal to 1. Proceeding in this way, or to say in a more precise terms, using mathematical induction, we can show that each QK is of rank less than or equal to 1. And whatever we have done for each PK, we can do similar things for each QK. But this time, we instead of using the equation M inverse M equal to I, we use the equation M into M inverse equal to I, and then proceed in the similar way of comparing the columns, we compare the rows. And it's essentially the same idea. We can do that each QK is of rank less than or equal to 1. And I think that completes the proof. So, okay, now let's see some examples. Suppose L2 denote the Hilbert space of these fusions, square integrals, sequences, etc. And even E2 is orthonormal basis. Let's look at the famous right shift operator. That is, if x is the vector exponential, etc., right shift makes the first entry 0 and then shifts all entries to x by 1. So R of x will be 0, etc. And take any real number with absolute value less than 1, and you take t is equal to I minus c times r. Then such a operator has to be invertible. Then the matrix of t with respect to the orthonormal basis t is tridiagonal and is given by this. All the diagonal entries are 1, and below the diagonal all are minus c minus c. Of course, it requires some work to calculate, but it's not very difficult. It can be easily checked that T is invertible, and the matrix of T inverse is infinite sum sigma C power j r to the power j going from 0 to infinity. And then the matrix of T inverse with respect to the orthonormal basis is, you get like this. The first row is 1 0 0, then or you can say first column is 1 c c square, etc. The second column is 0 1 c c square, etc. Similarly, all other columns, etc. And now you will see that, of course, it's trivial to see that all the submatrices lying above the diagonal are of rank. In fact, they are of rank 0 because only in which there are 0. If you look at below the diagonal, if you look at any submatrix, you will see that each row is a multiple of just one particular row because it will see is square, etc. Okay, I think this I will see. It is also easy to see that this above proof can be easily modified in an obvious manner to a natural generation that allows matrix M of t to have a wider rank. Instead of tridiagonal, suppose we say that so M is the matrix with the entries Mij. Suppose Mij equal to 0 or more, I can say bigger than P. For example, P equal to 1 corresponds to tridiagonal matrices. Such matrices are called prime matrices, and we can use similar theorems for M inverse, that submatrices of M inverse, this time not lying above or below the main diagonal, but we have to include a few more diagrams. Now, we can also observe by carefully looking at the proof that I mentioned just earlier, that in order to prove that each PT is a Frank equal, we only use the equation n inverse n equal to n. And similarly for 2k, we use the equation n into n inverse 2k. So essentially what we have proved is that we take okay, let me just take it here. Again, let X be a banana space, etc. And suppose the matrix of T with respect to A's diagram. If T has a bounded left inverse S, then every submatrix of the matrix of S with respect to A that lies on or below the belt diagonal is a Frank left one to two. And a similar statement about the right inverse. Not I should not say D or the right inverse. Left inverses can be many, similarly right inverses can be many. But this statement will be true for each of the left inverse and similarly for each of the right inverse. Again, we can see here, I just mentioned right shift operator in a few slides, right? Its left inverse is left, and it is easy to see that every submatrix of the matrix of L with respect to A that lies on or below the belt is a Frank left. This is another trivial example. Now, what we can say is try to see something more. That is, this left inverse or right inverse. Those are specific instances of bigger family of what are called generalized inverses. The question is there an analog of this theorem for other generalized inverses, and in particular for Moore-Penrose pseudo inverse? Now, some such results are known for matrices, and you can see this paper by Mr. Buffett. I mentioned a bit earlier because I came to know about this theorem through attending this lecture. So he has written a paper that generalized inverses of finite matrices, where again, similarly, the results are about the ranks of submatrices. Now, the question is whether we can have similar results. See, the generalized inverses and including Moore-Penrose inverse, that idea is also known for infinite matrices, that is operators on Banach spaces or Hilbert spaces. So the question is, do we have similar analogs for these cases of these operators on Banach spaces matrices with respect to them? So as of now, I don't know the answer. Yes.
Does anyone have a question?
If you mentioned that that can be true for all.
This one, Buffett.
No, before that, consequences of the what it has done is to every right.
Ah, yes. Yes.
There are two different inverses for same matrix.
That I can say from this theorem is that the submatrices lying below the belt diagonal will be of rank left or equal to 1 for all left inverses. And similar case for, but whether there is any relations between those two left inverses and all, maybe I don't know.
This would be one similar.
Yes, this would be one similar. Right.
These results are true for separable inverse.
If you want to write matrix, you have at least order basis. And in particular, separable inverse. It can be a Banach space with a order basis. It's a countable set, okay, such that suppose it's a Banach space. You take a countable set, and you can express every x in A as sigma alpha I AI. Infinite sum sigma alpha conversion infinite sum in a unique way. Okay? That is order basis. It's a linearly independent set. Linearly independent infinite set. And each x can be expressed as a sigma alpha x. And unlike the usual Hamel basis, where it is a finite sum, order basis you express as an infinite. Conversion depends. No, there are examples of the next basis where such order basis doesn't exist. And the whole thing that we need to deal with order basis is that in general the Banach space, not in the in fact, Banach space it is not finite dimensional, then it cannot have a countable Hamel basis. So we have to deal with order basis. And again, as I said, not every Banach space is order basis. There are examples where it doesn't.
Every inverse space.
No, separable, very separable. In fact, in case of Banach spaces, it is also even a separable Banach space may or may not have a order basis.
The orthonormal basis you do.
Orthonormal basis is a order basis. Separable. So yeah, in case of separable Hilbert spaces, it will have a countable orthonormal basis. Yes, and so it's
yeah. So Hilbert spaces is uncountable.
The examples that you have taken tell you that's it has a countable.
Okay, thank you, sir, for the very nice talk and a smooth passage from linear algebra to infinite dimensional. How do you land up from linear algebra into functional analysis was given by Professor Kulkarni. So let us thank him once again for a wonderful talk. Thank you, sir.
May I now invite Dr. S. Rane to kindly present a token of appreciation to our speaker.
So the next talk by Professor Shantanu Dey of IIT Bombay, and to talk about him, he's a professor in the Department of Mathematics of IIT Bombay, and we have already seen he did his PhD from ISR Bangalore, and we have already seen example of the bounded linear operators on a non-linear space. In fact, that forms Banach algebra, and then his work, his area of research is on C-star algebras and multivariable operator theory and so on. So he has numerous research publications to his credit. So I welcome Professor Shantanu Dey to deliver his talk on block quantum dynamical semigroups of completely positive definite kernels. So, welcome.
Good morning, all. So, thanks, Akshay, for the introduction. I thank the organizers for having me here. So, we start with this well-known result from operators on Hilbert spaces. Suppose we are having a block matrix consisting of x, y, adjoint of y and z defined on the direction of Hilbert spaces h1 direction h2. If this block is a positive matrix, if and only if x and y, that is the diagonal, are positive operators, and then you have a operator d from Hilbert space h2 to h1, which is a contraction, and the y that is appearing here is related to the d by the square root of the operator x and the square root of the operator z. So y is equal to square root of x d z square root of z. So positive operators have a square root. So in this talk, we'll address similar questions for completely positive definite kernels. I will introduce what they are. Till now, what I talked about is operators of Hilbert spaces, this one. So I'll introduce what is a C-star algebra. So it's a complex normed algebra which is complete and it has a conjugate linear involution, which is also called the adjoint and which satisfies the following properties. So this is the norm of AB is less than or equal to norm of A, norm of B. Then A adjoint is equal to A, AB adjoint is B adjoint, A adjoint, and the norm of A star A is equal to norm A squared. So we come across several examples of C-star algebra. So bounded operators on a Hilbert space H, that is a C-star algebra with respect to the operator composition, the addition of operators, scalar multiplication with an operator, and the adjoint operation. So this is a non-commutative structure, and this is a commutative C-star algebra. There are the continuous functions on the interval 0, 1. There are several other examples. So I gave one non-commutative example, one commutative example of a C-star algebra. So we need this notion for our work here. So next I define what is a completely positive map. So first of all, in B of H, bounded operators on a Hilbert space, we know what is a positive operator. It's like positive definite matrices similar positive operator. So a map between two C-star algebra or two from B of H to B of H, we say a map is positive if it takes positive elements to positive elements. Right? Now I'm talking about complete positivity. So complete positivity means suppose A is a C-star algebra, then MNA is also a C-star algebra. That is, if you take the matrix where the entries are coming from that algebra, that also forms a C-star algebra. So a map from, say, a map phi from A to B is said to be completely positive if the amplification to the matrix, so MNA to MNB, on that I can define amplification of the phi map, that is also positive. So at every level it is positive, that's completely positive. It can be concisely expressed in this way. So phi is completely positive, is ij running from 1 to n summation. Bj star phi aj star ai bi is greater than or equal to 0. It is stronger than positivity. Where bi's are coming from the C-star algebra B and ai's are coming from the C-star algebra A. So completely positive maps play an important role in quantum statistical physics, in operator algebras, as well as quantum information theory. So channels, they are completely positive maps. So this notion can be generalized to what is called as CPD kernels. So CPD kernels is defined in this way. So if you have A, B, two C-star algebras, and S is a set, then the function K from S cross S to B of A to B is said to be completely positive definite kernel or CPD kernel over the set S if this condition is satisfied. There is a summation over Ij, and you have similar to this condition Bj star K sigma J sigma I, Aj star Ai Bi is greater than or equal to 0. You may notice that this is a generalization of this. If you have the S to be singleton set, then what you get is the completely positive map. Then there is no choice for the elements to be chosen from S, and then it is the same thing. So here sigma is coming from this set S, Ai is coming from C-star algebra A, and Bi is coming from B. So completely positive definite CPD kernels become useful in operator algebras many times to address certain results about completely positive map. When you study completely positive map, sometimes we need little abstract setup. At that time, we need to introduce this. And several good results have been proved using this. Okay, so this is what is CPD kernel, and using this. Here is the notion of Hilbert module. So I have to introduce some heavy machinery in the beginning. So Hilbert module is like somewhat like the Hilbert spaces. So it has an inner product. So it is, so suppose B is a C-star algebra and E is a vector space which is a right B module. That means when you multiply it from right by the C-star algebra elements, it remains in the same space E. and it satisfies this relation what is given. So B is an element of the C algebra, X is an element of E, and the product this XB is again in E, and it satisfies this condition. And we have this inner product, but this inner product is B valued inner product. Usually the inner product is in C, right? But here it takes value inside the C algebra B. So it satisfies this usual condition which satisfied more or less in the Hilbert spaces also. So inner product of X is positive, the positive element of the C algebra. If it is inner product is 0 for XX, then X has to be 0. This is the convolute. Then you have this right linear with respect to the C algebra element B. You have this conjugate relation here, and I am assuming linear on the second coordinate. So this mu and nu scalars are coming out without conjugate on the right hand side. The left hand side coming conjugate. So this, if all these conditions are satisfied, then I call E to be a Hilbert module. So okay. So this is called inner product B module, and it gives rise to a norm in this fashion. So if X is an element of E, then the inner product XX norm and its square root, that gives a norm. And if this structure is complete with respect to this norm, then I call it as a Hilbert module. Otherwise, it has inner product, but it's not necessarily complete. So
this E is a complex vector.
Yes, it's a complex vector space. In addition, it's a B module also, and it has this inner product. Okay, so what till now we have introduced C algebra, we have Hilbert modules, and we have introduced CPD kernels. Right. So now the Hilbert B module that I call it, here I call it Hilbert B module. The B is the C algebra. Now we can have something called Hilbert AB module. So there is an action of B from the right hand side. There can be an action of another C algebra A from the left hand side. That is AB module. So let A be C algebras, and Hilbert AB module is defined as the right Hilbert B module E together with the homomorphism phi from A to BAE. Is a homomorphism here to the bounded adjointable operators on E. So when you take the bounded operators on E, they are not always adjointable in this structure, unlike Hilbert spaces. So this is additional assumption we have to make. So this is a star homomorphism. Then the left action of A on E reduced by this phi is given by this. AY is equal to phi AY. And so now we have two C algebras, and together with their actions, we have a Hilbert AB module. This is a result by Barreto, Bhatt, Lipscher, and Skyday. This gives a decomposition of the CPD kernel. Suppose K is a CPD kernel from S cross S to BAB. Then corresponding to a CPD kernel, there exists a Hilbert AB module, namely F, and there exists a function I from S to F, such that the CPD kernel can be decomposed in this way. So inner product I sigma A I sigma dash, where sigma dash are coming from S, A coming from A, with the minimal condition that F, the Hilbert module F, is generated by the elements of the type A I sigma B. So this is very much similar to what is GNS construction, what we do in C algebras. So kind of representation theorem. This is as for states, we have states on C algebra, we have GNS construction, and then for completely positive maps, GNS construction, there is something called Pascal's GNS construction for CP maps, and for CPD maps, we have this, and this result, so it's like a representation. And this, for a K, we get this F and I associated to it, which is called the Kolmogorov representation of the CPD kernel K over S. So now if we have a E is a AB module and F is a BC module, then we can define tensor product of E and F, E tensor F. So for elementary tensors X tensor Y and X dash tensor Y dash. So where X and X dash coming from E, Y and Y dash coming from F, the inner product is defined in the following way. The inner product of this is equal to inner product Y comma inner product of X dash Y. One can check that this is positive definite when we choose this to be same. And then we need to quotient it by this set N is equal to W E tensor F, where W is equal to 0. So the interior tensor product of E and F is defined as the completion of the quotient of E tensor F by N. That is denoted by E round circle F, which I will be referring to as tensor. Okay, so this is the interior tensor product of two Hilbert modules, and X tensor Y, X circle dot circle Y denotes the equivalence class of X tensor Y in this quotient data, that is the equivalence class. So this would need. So similarly, if you have E and F to be Hilbert AB module and F and F dash to be Hilbert BC module, then E tensor S from E tensor F to E dash tensor F dash is defined in the following way. So T tensor S over X tensor Y is EX tensor SY. So operators are defined on X tensor Y in the following way. Okay. On this preparations, also I need what is for polynomial modules we will need. As I told you that all the bounded operators from one Hilbert module to another Hilbert module may not be adjointable. But we can get adjointability if we assume one normal structure, one normal algebra structure and module structure. So here I introduce that if A and B are sister algebras, and suppose you have a representation of B on H, that bounded operators on Hilbert space H, then E tensor H forms a AC module, and we can define the left multiplication, left creation operator in this way. Lx H is equal to X tensor H. Lx is the element of the bounded operators from H to E tensor H. E tensor H is also a Hilbert space here. So it's H and this both are Hilbert spaces. Suppose B is a phenomenon algebra. So I'm assuming instead of sister algebra, phenomenon algebra. A Hilbert AB module F is now called a phenomenon B module if it is strongly closed in BH F tensor H. So here is the embedding of E into B of H to E tensor H. So this embedding is strongly closed. Then we call it one-normal B module. And the sum topology, that is what is referred to as strong topology. And now we can have one-normal AB module also. There we need the representation also to be normal representation, something compatible with the one-normal algebras. It is basically sigma weakly closed. So why I assume this structure is that in the one-normal modules, any bounded right linear map is also adjointable, which is not true in Hilbert module case. So now we come to our results. So what we want to do is today we want to deal with block CPD kernels, just like we have block operators in that way. So suppose A is the unit sister algebra, P1 is a projection in the sister algebra, and you take Q1 to be equal to 1 minus P1. So that is also a projection. So we decompose any element of the sister algebra in this way using the projections. So we get 4 corners P1A, P1, P1A, Q1, and so on. So you see each corners are in this respective parts P1A, P1, and so on. So this is a block decomposition of the given element of sister algebra. So when do you say that we have a block kernel? Suppose A and B are sister algebras, P1, P2 are projections in A and B respectively. Then a K is said to be a block kernel if K takes blocks to blocks. So suppose A has been decomposed in this block, right? So K, when acting on this respective blocks, takes it to another block here. This block generated by P1, and this is generated by P2, Q2. P1, P1, their projections. Block structure is preserved. So this kind of thing we want to deal with. Now this is the first result, which you can compare with the first result that I showed in the slide about block matrices. So suppose if we have okay, so let me display the whole thing. So we are talking about this block CPD kernel, right? I'm talking about a kernel, this K, and you have K1 and K2 on the main diagonals, and some other kernels K and K star of diagonals. So I'm trying to relate K1, K2 and this K to this. So let me go back. So suppose you have K1, K2, this two, K1, K2 to be CPD kernel with the holomorph representation I stated in the previously. Then this result, what it says is, if you have a V which is a bilinear adjointable contraction from F2 to F1, then you can get this whole kernel to be CPD. Initially, you are having only K1 and K2 to be CPD, and we are having this K, which is adjointable contraction. So the result says that if you arrange it in this way, where L is related to the V in this fashion, then this becomes CPD. This is one result we get, and the converse is also true. But the converse becomes true not in this setup. You have in addition assume that B is a phenomenon, because I will illustrate that with example also. So I'll show that converse now. So here what happened is K1, K2 was CPD, and we got this to be CPD if such a adjointable V exists. Converse says that suppose we have K1, K2 which is CPD, and we already have this to be block CPD, then it gives rise to existence of a bounded adjointable contraction V. Previously V was given, if V is there, then we have block CPD. Now it says if we have block CPD, then we have V, which has this property. Okay. But see, we have assumption that V here is polynomial algebra. By VNA, I mean the polynomial. It's not just instance algebra, it's a polynomial algebra. So you can, this result is not true when V is just C algebra always. You can see in this example. So suppose A, B, they are C algebra, this is commutative C algebra, and we continuous functions on interval 0 to 1. And E is a Hilbert module, also C on the continuous function on the interval 0 to 1. Then the inner product here is what? It's just the F conjugate multiplied with G, pointwise. When you multiply, you can get a continuous function. So, so you take one element from A, another element from. Sorry, you take F and G both from E and take the inner product. You get again an element of A here. Okay. So I will illustrate the previous theorem is not true if B is just C star algebra, and it is true if it is a polynomial algebra. So suppose you take H1 to T to be equal to T and H2 T to be equal to 1. There are two functions. So in this case, this, because it's 0, 1, so it's 1. The star is also same. So now I'm defining the, okay, so this example, I keep it simple. Instead of giving example of CPD kernels, I am giving an example of CP maps, because CP maps are special cases and the setup is simple in this case. So here we have M2A, which is also C star algebra, M2B, because this gives the block structure, and the CP map is defined in this way. Phi of this matrix in M2A is defined in this way as given. So we have this H1, H2 defined here coming on two sides. It is clearly completely positive. Such kind of maps are completely positive. You multiply, you get this. So this has a block CP structure. If I call this as phi 1, this I can call as phi 2 of F1, phi 2 of F22, they are completely positive again. And this is L and this is L star. Okay, this is a block CPD. And so corresponding maps are given in this way relations. Now I can do the, so I said if you have CPD kernels, then correspondingly I can have the Hilbert AB modules. So if you construct the Hilbert AB models, they will be precisely this E1 and E2 in this case. And they turn out to be continuous functions where F0 is equal to 0. it's clear why H0 is equal to 0 because H1 is of that type. H1 was HT is equal to T. Right? So because of that, this becomes this. But H2 was constant function 1. So therefore, E2 becomes the full A. Right? So it can be shown that there is no bilinear contraction, that V that I was talking about, there doesn't exist such a thing. Though it's block CPD, there does not exist a adjointable bilinear contraction. But now you see the B here is a C-star algebra. It is continuous functions on 0 1. This is C-star algebra. It's not a phenomenon algebra. If I replace this by phenomenon algebra, then you see the block CPD will correspond to a T. So if I replace the B by C by L infinity 0 1, this is an example of a commutative system, commutative phenomenon algebra. If I use this, then EIs will become L infinity 0 1, and in this case it can be shown that such T exists. In fact, in short, I will tell you the T basically takes 1 to 1, and that doesn't work here because though see 1 is not present here. Whereas here, since it is L infinity, T1 to 1 works. So this illustrates the phenomenon algebra is needed there. Okay, so the whatever result I showed you for CPD kernels also holds for semigroup of CPD kernels. So semigroup of CPD maps are also play important role in this quantum stochastical mechanics and operator algebras. So just like you have semigroup of CP maps, we have semigroup of CPD kernels also. The same way and equally useful. And this is how semigroup of CPD kernels are defined. So basically, it's a so here T stands for semigroup. Either you take the natural numbers with 0, or you take the positive real numbers as T. And for every T belonging to T, your KT is a CPD kernel. So you have a family of CPD kernels, which is semigroup. One parameter family of CPD kernels, a quantum dynamical semigroup over S is defined in the following way. You have this KT composed KS is KT plus S, K0 of W is W, and KT of 1 is equal to 1. This is quantum dynamical semigroup, and if KS is unital for every S, then it is called quantum Markov semigroup. Okay, so now for this also we have a similar result. First, note that to a quantum dynamical semigroup, we can associate an inclusion system. This is something called product system. So, product system is a special case of inclusion system. So, to semigroup of CPD kernels and to inclusion, they are connected to each other. So, here I start with okay, so I'm defining what is a inclusion system. Suppose we have a family of Hilbert BB modules and we have an alpha family, then this relation, if it holds, then it is called an inclusion system. Okay, so alpha maps satisfy this relation. Okay, now if you have an inclusion system and if you have a certain family of eta, which is a family of vectors, and we satisfy this alpha st, the inclusion system, this relation, then we say this eta is the unit for the inclusion system. And the unit can be generating. So this tells you that if you have an inclusion system like this, F alpha, then to that, from that I can get a quantum dynamical semigroup. This is justified here. So one thing I want to insist is that this slide. Yeah, so here bilinear isometries are there, alpha st, they are bilinear isometries, but for product system, they need to be unitaries, alpha st. So what this illustrates is that if you have QST, that inclusion system is associated to inclusion system, the QST is associated. This is also another representation kind of thing. Right, so the results that I showed for CPD kernels in terms of block CPD kernels. The same results also holds for block CPD semigroups. So if you have again, this is the block CPD semigroup. If you have KT1 and KT2, two block CPD semigroups, and if you have contractive morphism, some notion which is defined in the previous slide, then we can get the whole CPD block CPD semigroup. From CPD semigroup on the diagonal and this morphism, we can get a block CPD semigroup here. And the converse is also true when you assume von Neumann algebra. So B is a von Neumann algebra when you assume. Then if you have a block CPD semigroup, and then you associate with that, we get unique contractive morphisms, which are bilinear isometries. So the results what we prove for CPD kernels also prove for block CPD semigroups. How much time you have? 5 minutes. Okay. So there is some other notion called phi maps. So suppose we have a Hilbert C-star module E and F over C-star algebra B and C. So a map T from Hilbert space E to F is said to be a phi map if phi preserves the inner product. So this is the inner product in E and this is the inner product in F. So phi preserves the inner product in E to the inner product with respect to T in F. That's called phi map. So Steinstein theorem, that is popular result in operator algebras, has been generalized as phi maps by Professor Bhatt, Ramesh, and Sumesh. So similar notion is there for K families also. Similar notion is there for CPD kernels also. So suppose we have a kernel K S cross S to BC and K sigma are maps which satisfy this relation, again preserving the inner product, then we say this family is a K family, like phi maps K family. So with respect to that, we have this S.I.W.S factorization theorem, which tells you that if you have a CPD kernel and if you have K sigma with a K family, what is the meaning of this statement? That K sigma preserves the inner product. So let me just recall that this property is satisfied. That is what is claimed in the first statement. If this property is satisfied, then we have a factorization of the K family in this way. So there exists a isometry V from the Hilbert module such that K sigma factorizes in this way. Okay. So with this, we have this last result, which says that if K is a Hilbert C-star module, if we have a K family of linear maps, and if epsilon T is the span of KT XB given in this way, then suppose K is a CPD kernel over S such that the semigroup of K families we have, suppose we have CPD kernel and the semigroup of K families we have, this is if and only we get a block CPD kernel semigroup, blockwise semigroup of CPD kernels in this way, from this structure to this structure. So these are called the linking algebras. So this result means that the KT can be extended to a block CPD kernel. So, okay, so that's all we have in here. So there are some references.
Questions, if any? What are the examples of non-commutative Hilbert C-star models?
Well, C-star algebra itself is an example. C-star algebra itself with the treated as a Hilbert model.
Similar thing can happen in these AB models.
Yeah, so you just need a representation. No? Just,
So can it happen that in this AB models, one is commutative and other is non-commutative?
AB modules. One is commutative and the other is non-commutative. Should be possible. Don't know whether it immediately or not. It's a great example. Yeah.
I just one more question. Is it correct to say that we commutative for diagonal algebra is something L-infinity on some Lie space?
Yes, commutative phenomenon algebras are L-infinity space.
Thank you.
And my question is, why is there any specific reason for choosing the inner product writing it to the second variable?
Well, I think the physicists prefer that structure because many things fall in line in that case. Especially, yeah, rank one operators can be very easily written in that language.
And the star is the conjugation, is the usual conjugation.
Star is the adjoint operator for B of X. It's the adjoint of B of X.
So I think, so we have already seen in our MSc class, we started from Ray's representation theorem, and then we saw that for Hilbert spaces, the life is easy, that you know that the adjoint existence is bounded. But then we see that when we complexify structures, how one has to go about it and have representation theorems in this case. So I thank Professor Shintamide for illustrating and with nice talk. Thank you, sir.
May I take this opportunity to invite Dr. S.I.W.S to kindly felicitate our speaker with a token of gratitude.
So it gives me immense pleasure to invite my supervisor, Professor Rekha Kukul. She did her PhD from IIT Bombay, followed her second PhD from Grenoble, France, and her area of research is numerical functional analysis, time theory, and operator theory. So today, now she is visiting CEBS Mumbai, and today she will talk on approximate solutions of weakly singular integral equations. So I welcome you.
Hello. So thank you, Akshay, for kind introduction. I would like to thank organizers for giving me an opportunity to give a talk here. Hello. Hello. We will talk about weakly singular integral equations, Fredholm integral equations. So we will talk about Nystrom method, which is mainly for smooth kernels. Then product integration method, which is adapted for weakly singular integral equations. For the product integration or for weakly singular integral equations, we need to take graded mesh. Then there are some two-grid methods which I will describe briefly and some numerical examples. So the setting is X is C01, continuous complex valued functions defined on interval 0, 1, and the norm is the maximum norm. This is the integral equation, integral operator. So it is assumed that the kernel is continuous. So T will be a linear map from X to X. It will be compact, and consider the operator equation lambda u minus 2u is equal to f, where lambda is not an eigenvalue of T, which will guarantee that this equation has a unique solution for every f in C01. Now, for weakly singular integral operator, there are conditions on the kernel. The first condition is this supremum should be finite, and then limit h tending to 0 plus supremum taken over mod of s minus s dash less than or equal to h, and this integral, the limit should be equal to 0. In that case, also T is a compact linear map, and examples of weakly singular integral operator, there are sort of two classes, algebraic singularity or logarithmic singularity. So these are the two singularities which we consider. Now, some notations. So resolvent set of T is set of all Z such that T minus Zi inverse is a bounded linear operator, and spectrum is complement of the resolvent. And T compact will mean that every non-zero spectral value is going to be an eigenvalue of finite algebraic multiplicity. So actually there are companion problems. We are going to consider operator equation. So since lambda is in the resolvent set, this has a unique solution. But this is the equation on infinite dimensional space, and very rarely you can find the exact solution. So one tries to find an approximate solution. So for that, look at a sequence of finite rank bounded linear operators. Afterwards, I will specify a choice of such TNs. And then this Tn should converge to T pointwise, and also norm of T minus Tn into Tn should converge to 0 as n tends to infinity. In that case, we are assuming that lambda is in the resolvent set of T. So for n big enough, lambda is going to be in the resolvent set of Tn, and the inverse lambda minus Tn inverse, that is going to be bounded uniformly with respect to n. So norm of lambda minus Tn inverse is less than or equal to C1. And then this lambda un minus Tn un is equal to f. We'll have a unique solution. So this un is going to be an approximation of u, and more importantly, un is computable using computer. So since Tn is finite rank, this lambda un minus Tn un is equal to f can be reduced to a system of algebraic equations. And then by solving that, one obtains un. Now about the convergence. We have lambda u minus 2u is equal to f is the exact equation. Lambda un minus Tn un is equal to f is approximate equation. So u is going to be lambda minus T inverse s, and un will be lambda times identity minus Tn inverse s. Then using so-called resolvent identity, you get lambda I minus Tn inverse into T minus Tn into lambda I minus T inverse S. This can be easily proved by adding and subtracting lambda times identity in T minus Tn. Now lambda I minus T inverse S is U. So you have this. Now take norm of both the sides. Norm of lambda I minus Tn inverse is less than or equal to some constant C1. So you have norm of U minus Un infinity is less than or equal to C1 times norm Tu minus Tnu. Tn is converging to T pointwise. So norm of Tu minus Tnu will be tending to 0. Also, by looking at this norm of Tu minus Tnu infinity, we can find order of convergence. So, first I am going to describe the Nystrom method where T is replaced by a quadrature rule. So, consider space Xn to be piecewise constant functions and look at the midpoints of each subinterval and then approximate integral 0 to 1 ut dt by integral 0 to 1 pi ut dt. So this will be equal to, now split the integral 0 to 1 over ti to ti plus 1 and u of Si pi nu on the interval ti to ti plus 1 pi nu at t is equal to u of Si. So now this is of the form summation wi usi, where wi's are going to be 1 by n. Then there is trapezoidal rule. In that case, Xn are continuous piecewise linear functions. In case of midpoint, they are piecewise continuous, not necessarily continuous. And there are Gauss 2-point rules. So Gauss points are zeros of the Legendre polynomial. And you again have some approximation of the integral of this form. There are weights and there are values of u at some points. So this is what one, and then also about the order of convergence. Norm of pi u minus u infinity is less than or equal to constant times norm u dash infinity into h. So if your u is differentiable, then the convergence is of the order of h. Now you are replacing in the integral ut by pi ut because of the symmetry. Even though norm of pi u minus u infinity is only of the order of h, for the integral it becomes h square. H square is going to converge to 0 faster than h. You need u to be 2 times differentiable. Then for the trapezoidal rule, there is whether you take norm of pi u minus u infinity or error in the numerical integration, both are of the order of h square. Whereas for the Gauss point, again the pi u minus u infinity is of the order of h square, but because of the special property that Gauss points are special points, those are the zeros of the Legendre polynomial. So you are going to get constant times h raised to 4. Now in all this, you need u to be sufficiently differentiable. So the Nystrom method, it is, look at t is our integral operator, integral 0 to 1 ast x to dt, s is fixed. So replace the integration by numerical integration. So that is what will give you a operator Tn which is of finite rank. It will satisfy the conditions which we needed. And then you will have, for example, for Gauss point rule, norm of u minus un infinity is less than or equal to constant times h raised to 4. But this differentiability of U is important. Now, if the kernel and function f, if both are smooth, the jth derivative of Tx will be given by partial derivative of K with respect to S of jth order. And then that will make U to be smooth. Now this breaks down for weakly singular kernel. Look at xt is equal to L1. It is a constant function, whereas if you take the kernel to be log of mod of s minus t, then you are going to get this. So your Tx, it is going to have singular behavior at both the points. So that is why you cannot apply the Nystrom method. That means just replacing integration by numerical integration does not work for weakly singular kernels. So now in the product integration, what is done is choose xn to be space of piecewise polynomials of degree less than or equal to r minus 1 with some partition of interval 0 to 1, and then we choose r collocation points or interpolation points in each subinterval, fit a polynomial, and then so you can write pi n x and t to be in terms of value of x at Fij, and then apply this only to x. That means keep k of st as it is. Earlier we were looking at the function s fixed ast xt, replace it by numerical integration. Now you are keeping kst as it is and then applying it only to x. So you are going to have this integral 0 to 1 kst eta ijt dt. The kernel is given to you. Our kernel is either mod of s minus t raised to alpha or log. So these are the weights. They will be calculated exactly. So this is known as product integration. So this whatever I have written in the red, so that is going to be W-I-J-S. It is independent of X. It depends on kernel and it depends on what your piecewise polynomial space is. Eta ij's are going to be basis functions for that. And then it will again satisfy the condition which we wanted. So this amounts to replacing T by T by N. So now, like this is just illustration how you reduce it to algebraic system. T pi n x is of this form. You are looking at UNS minus T pi n UNS is equal to Fs for each s belonging to 0 to 1. So put s is equal to SLM, and then this is the algebraic system you are going to get. Solve it, and once you obtain UN at SLM at any point S, it is obtained by this equation UNS is equal to T pi n UNS plus Fs. This is just to show you that it is computable, because that is very important. We want to find approximate solution by choosing n big enough, which is an acceptable approximation. Now, the computation of weights, that is a bit delicate. So, for the piecewise linear interpolation, this integral 0 to 1 lit log of mod of Ti minus T dt, those are going to be our weights. This, whatever I was calling eta ij's earlier, here now these are lits, the basis function, and then you will get formula of the type Wij x at Ti. So now here you have T minus Ti minus 1 into log. So as such, you have standards for, you know how to do it, calculate the integration by parts. But if you apply those formulae, there is loss of significant digits. So when you write program, you have to be careful and evaluate or compute the weights in a different manner. So now, for the non-smooth functions, like if you consider piecewise constant function, if function is differentiable, norm of pi u minus u is less than or equal to constant times h. But suppose your u of t is equal to root t, then this order of convergence h gets reduced to root h. So that is where the need of graded partition comes into picture. So by choosing, instead of taking uniform partition, wherever there is singularity, you add more number of points, and then you can restore the order of convergence. So these results, they are like you take the graded partition with parameter q, and then like if you are considering piecewise polynomials of degree less than or equal to r minus 1, you expect the order of convergence to be 1 upon n raised to r. So by choosing the q, the parameter, like this is the graded mesh, when q is equal to 1, what you get is uniform partition. So by choosing this, like in case of algebraic singularity, choose your q to be bigger than or equal to r by alpha, or if it is log, then choose q bigger than r, then it restores the order of convergence. And then for Gauss points, those are special points, so there you can get some additional order of convergence. So instead of n raised to minus r, you get n raised to minus r minus alpha. So now the idea is you are replacing t by t pi n, and then you are going to get a system of equations which you solve, and you are going to get order of convergence, or you are going to get approximate solution. But then for weakly singular kernel, the convergence is slow. So in order to have the required accuracy, you may have to solve a very big system. So what one tries to do is that big system you approximate by a smaller system, and then on that you do some post processing. So you have T to be weakly singular integral operator. Forget about that and now concentrate on T pi m, where m is big. So this lambda um minus T pi m f, that will be a system of size m if you are considering piecewise constant or higher. Now you look at the n to be smaller, and you look at T pi uns. Now this T pi you are going to approximate by another operators. So in the collocation method, or now discrete collocation method, you apply pi n on the left and on the right. These are some classical methods. And then sometimes by one step of iteration, you get better result. Actually, if your kernel is smooth, then it is always going to get better result. Here, it depends on what points you are considering. And then this is so-called modified projection method, which I had proposed some years back. And it worked very well for smooth integral operators. But even for weakly singular integral equations, you get better results. And then here you can also again take the iteration. So these are the orders of convergence we would prove that if your kernel is 1 upon root of mod s minus t for continuous piecewise linear, the collocation and iterated version order was n raised to minus 2, n tends to infinity. So n raised to minus 2 tends to 0. And for UNM, it is n raised to minus 2.5. So the improvement is not spectacular as in case of smooth integral operators, but there is improvement. Then there are similar results for piecewise constant and for Gauss points. So now I want to come to the numerical results. So I will just quickly tell you the two-grid method. So you have lambda um minus t pi m is equal to s. That is the big system which you want to solve. Now you consider Tn. So Tn will have a small rank. Like the numerical results which I am going to show you, m is 256 and n is 4. So by solving the system of size 4 by 4, you get approximation for the system of size 256. So now here, take an initial approximation and calculate the residue that f minus c. If your um 0 is equal to um, this is residue will be 0. But now it is only an approximation. So there will be some residue r 0. And then you will have um minus um0 to be lambda minus t by u inverse r0 approximated by some lambda minus tn inverse r0, and that will give you the next one. So this is what is two-grid method. At each time rk, you are going to calculate residue. So there will be t pi m coming into picture. But there will be, you are not solving the system, you are only doing matrix into vector multiplication. And then in order to calculate umk plus 1, you need lambda minus tn inverse rk. So that is where you need to solve a system of equation. And that is going to be of size small. So that is going to be, say, 4 by 4. So there are some two methods. And you have norm of I minus pi n t. T is a compact operator. Even for weakly singular integral operator, T is compact. Pi n converges to identity pointwise. So norm of I minus pi n t tends to 0. So this um tilde k plus 1 is k plus first iterate. That error is going to be smaller than the error at k. And in case of discrete modified projection method, instead of the factor norm of I minus pi n t, you get norm of I minus pi n t square. That is why you are getting faster convergence. So these are some of the numerical results. So KST is the kernel 1 upon root of mod of s minus t. UT is the, I have chosen right hand side so that UT is root t plus root of 1 minus t. So this typically illustrates what is going to happen. And then these are the results. So see, even collocation method too. In 7 iterates, your error is of the order of 10 raised to minus 9. Whereas in the modified projection method, if you do, say, 4 iterates, then you already reach 10 raised to minus 10. And when you do 7 iterates, it is the order is 10 raised to minus 15. It was done in the double precision, so this is the best. Means after 10 raised to minus 15, it is considered as 0. So by performing 7 iterates, for each iterate you will be solving a system of size 4, and you are getting the results as good as for solving a system of size 256. So that is the advantage. And as I said, the writing the programs for this, you have to be careful about the weights and about everything. But this is illustration. It works. So these are some of the selected references. The graded partition idea that was of J.R. Rice. That is something classical, and also Schneider. And our contribution is about 2-grid method. So thank you for your attention.
Hello. 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 Questions from the audience?
And with the grid mesh, if we have some singularities, then how could we identify those singularities in the intervals, like by using
Yeah, so singularities are going to be, see, like this, I have given that 1 upon root of mod of s minus t. So your solution will have singularities at the 2 endpoints, and that affects the order of convergence. That is why one considers graded mesh, where uniform mesh is throughout. Whereas for graded mesh, towards the left hand and towards the right hand, there are more number of, you make the length of the subinterval small, and that compensates for the order singularity.
So I take the L shape domain. So I need to understand that in the corner of the L shape, there will be a singularity. But
so you are talking about 2-dimensional. Yeah, so there at the corners you will have to take more partition points or more grid points.
Is there any error estimator to identify them, those intervals, such intervals?
Yeah. So actually that will be the generalization for 2 dimensions. But generally what works here, if you are taking tensor products, it works for that one.
You are saying about the geometry of the figure. Geometry can identify where are the corner points. You are given the geometry. So, for instance, polygonal domain. The corner points are going to be off.
See, if it is a rectangle, you will be taking uniform grid. Now, if you are taking L shape, there is this corner. So now you choose, like, take the wherever there should be more partition points in that neighborhood. You are taking now, anyway, you will be taking partition of your L-shaped domain. So you are taking the partition of x-axis, partition of y-axis, and then take their tensor product. So there, that one, whatever the response, take more number of points. Partition points.
So one thing, the modified projection method, Madam has proposed is called as the Kulkarni method. I mean, it has done wonders, and we are working on the reciprocal expansions for eigenvalues and operator, and even in the similar cases, it is working well. So let us thank Professor Thirumalai for a wonderful and useful talk.
Let us now welcome again Dr. S.I.W.S to come forward and extend a token of appreciation to our honored speaker. We now move to session 1B, which continues our theme of mathematical analysis with contributory research presentation. Once again, I invite Dr. Akshay S. Rane to chair this session and guide us through the talks.
So I invite Shashank Shukla to deliver a talk on note on improvement of iteration, the approximate solutions of second-kind Fedorov integral equation with mean self-reference.
Good afternoon, everyone. Good afternoon, everyone. I am going to present our research work on a note on improvement by equation for the approximate solutions of second-kind Fedorov integral equations with Green's converse. This work is focused on approximate solutions of integral equations. Basically, we are finding the rate of convergence, order of convergence by using techniques of numerical functional analysis. So these are the outlines which will follow. First, we will discuss the Fedorov integral equations of the second time. Then we will move to the interpolatory projection, and further we see some two results for smooth kernels. The results are about the rate of convergence, and then we will move to our research concern on base kernel. Then we will see some required lemmas and proposition proposed by us, and finally we will see our results and we will validate it by an example. So we have to firstly consider X be the space of continuous real valued functions defined on 0, 1, and omega be this square region. We are considering here the space X with supremum now, and suppose the kernel function is here kappa and it is continuous about this square region. We define this integral operator in this way, and since kappa kernel is continuous, hence the operator must be compact here. And this is a Fedorov integral equation. It is actually of second kind, and we can when we employ this integral operator, we can briefly write it in a form of many equations. And here we take an assumption. We will take one is not an eigenvalue of the linear operator k. It means the operator I minus k is continuously invertible. And in this case, if we take f sufficient of f as required smooth, we will have the unique solution for the main equation. And this is an example in which the kernel is smooth. You can see st is raised to st by 5. The kernel is smooth, and here exact solution is given. Actually, such type of equations are important, and it naturally arise in physics, boundary value problems, and sometimes in engineering applications. So here we what happens actually, most of the times we can solve these problems, we can find the exact solution, but sometimes it is challenging to find the analytical solution, exact solution. In that case, our focus turns towards the approximate solutions. So we convert it into as an approximate equation where we take phi n to be finite range projection operator that pointwise converts to the identity operator, and here phi n is approximate solution, and we choose this projection in such a way that our approximate solution converges to the exact solution uniformly in the sense of supremum norm. So now here projection methods come in picture, in which we replace this this integral operator with Kn, where Kn is either pi n k or k pi n, and it may be combination of pi n or k, pi n and k. So now there are actually basically two projection methods. One is Galerkin, and second is interpolatory projection. In Galerkin method we use orthogonal projection, and in interpolatory projection we use collocation method we use interpolatory projection. So first we will here we will discuss interpolatory projection. Actually our research is based on the interpolatory projection. So first, we consider the uniform partition of 0, 1 in this way, where the mesh length is 1 by n, and if you denote the subintervals by delta j tj minus 1 minus tj minus 1 or tj, and if we take r with a positive number, then we can construct approximating space in this way, where we choose x be a polynomial of degree less than or equal to. So basically we are taking the space of even degree polynomials, and we can choose these interpolating points. We are doing interpolating projection, so we need the interpolatory points to choose a collocation point, and we have to fit an even degree polynomial. Here we are taking collocation points in such a way that the points are equidistant. We are taking 2r plus 1 points in each subintervals, and these points are equidistant with the distance of, I think, 1 by 2r. Here we define the interpolatory operator Pn from x to xn in this way, and by using Hahn-Banach extension theorem, we can extend this Pn to L infinity 0, 1, and hence Pn will be projection here. And this is a well-known result. If we take x smooth 2r plus 1 or delta j, we have this bound. These are the proved results whenever the kernel is smooth. The first equation, approximate equation for the first equation, that is a collocation equation proposed by Atkinson, and you can see here the order of convergence for collocation solution. Hence is actually collocation solution. It is 2r plus 1, and the one-step iteration is defined as the Swamy solution, iterated collocation solution. It is finest, and you can see here the order of convergence in this case is 2r plus 2. The modified method, projection method, was proposed by Kulkarni ma'am, and you can see the equation for the modified projection method. It is phi is minus km phi, where km is this projection operator pnk plus kpn minus pnk pn, and by Ramesh in 2017, it has been shown for the smooth kernel the order of convergence in modified collocation solution. Phi is modified collocation solution. The order of convergence is 4r plus 3, and the iterated version shows the order of convergence is 4r plus 4. These are the references. Okay. So our focus turns toward the non-smooth kernel, particular type of kernel, that is Green's function type kernel. We have done we have done actually the non-smooth part of. Here we see the Green's kernel. This one actually kappa is defined in this way. K1 is continuous throughout throughout the domain linear, and K2 is continuous in this domain. And if on the diagonal K1 is equal to K2, then we can refer such functions as kernel, as Green's kernel. And for example, we can see a second time Fedorov integral equation, including with Green's function type kernel. Why our research is important? Actually, when we consider from where such type of integral equations comes into picture, when we see the 2-point boundary value problem, we can convert them into integral equations, and there are such kernels comes into picture. what happens why we use projection methods? Actually, solving such two-point boundary value linear ODE, right? Through well-known methods of finite elements method, finite difference methods are challenging sometimes. Then we will convert those equations into integral equations and we apply our projection methods. Basically, the known methods, collocation and Gaussian methods. So in our study, we have done the collocation methods. Okay. So these are the lemmas, required lemmas, which we will use in constructing our propositions, and finally we will use this in our error bounds in our main results. So actually we are taking here the divided difference. These lemmas are based on the divided difference of kx at collocation points, and we have proved in our paper. The proofs involves elementary analysis, and we are skipping here proofs. These are the three crucial propositions proposed by us in our paper, and this will be the backbone for our main results. The first one will give the error bound for the Sloan solution. The second one gives for the modified solution, modified collocation solution, and the third one will provide for the iterated modified collocation solution. Okay, these are the all main result, which which gives the error bound for the collocation function. Means it gives the rate of convergence when the kernel is of Green's type. Here you can see when we are taking the approximating space given degree polynomial of degree 2 up to degree 2r, we can see the collocation solution INC as rate of convergence as x raised to 2r plus 1. And similarly for iterated collocation solution, finest we can see here the rate of convergence is h raised to 2r plus 2. Clearly we can see the iteration improves the rate of convergence. And for modified collocation solution, here for phi NM, you can see the rate of convergence is h raised to 2r plus 2, and similarly for iterated version, phi NM denotes the iterated modified collocation solution. The rate of convergence is again improved, it is 2r plus 3. And whenever we consider the case r is equal to 0, that is the space of piecewise polynomials, piecewise constant functions, then we can see the order improves. Whenever we take iteration, it is h2 for the modified collocation solution and h raised to 4 for iterated modified collocation solution. These are the sketch of proofs, and we have validated our result to a numerical example in which we have chosen the space of piecewise constant functions, and we have taken this interpolatory projection. And for this example, again we have this same this example. For this examples, we have computed the order of convergence, and hence we find the order of convergence for collocation, iterated collocation, modified and iterated modified collocation. It is 1, 2, 3, and 4 respectively. So, what is the advantage of our study? Actually, we see what happens when we choose the cost points. When we choose collocation points as cost points, we see the moment occurs. Whenever we go to collocation to iterated collocation, modified to iterated modified, we see the improvement occurs. But whenever you take any ordinary point, cost points is actually basically the zeros of Legendre functions. Or whenever you take some special functions, zeros of special functions as collocation points, you can observe the improvement. But whenever you take the ordinary points, the iteration does not give any improvement. We have given example in our paper. But in our study, whenever we choose the polynomial space as approximating space as given degree polynomial space, we see the improvement occurs here. So this is the basic advantage of our study. These are our published paper, and our talk was based on this paper, and these are the references. Thank you.
Questions? Now let us thank the speaker. Next Next speaker is Dr. Govind Rakshit. It's from Rajiv Gandhi Petroleum Institute, IT, and the title of his talk is Discretization of Projection Methods to the Approximate Solutions of Linear and Non-Linear Integral Equations for the second time. Thank you, Akshay and presenting. So I'm going to talk about the discretization of projection method, but just now Shashank and Professor Kukane discussed. So discretization, I will talk about projection method. So linear and non-linear integral equation. Let me introduce what is linear and non-linear. See, this is integral equation. First freedom integral equation. This is a linear. You can this kappa is called the kernel, and the hammerstring it is non-linear. And this is Euclidean integral equation. This is fully non-linear. Let's call this integral operator as k. Maybe either linear or non-linear. The second kind. Now, method of approximation. So we have Nystrom approximations and projection-based approximation. Nystrom approximation means when we replace these integrations by some numerical formula, and projection-based method means when we approximate this k, this operator k, by using some projection. So we define our approximate equation like this, and we'll find a solution. We'll find a solution of this, and we'll show that solution converges to our exact solution of this equation. So this is our aim. So for that, to define this approximate solution, or say the kernel, the operator kn, this is an approximating operator of this k. So let's define an approximating space, which we are taking the piecewise polynomial space. It's a piecewise polynomial space of some degree r. So with respect to some uniform partition. So here we are taking piecewise polynomial degree less than equal to r. So it is finite dimensional space, and our dimension is n into r. So now let's define projection. So we'll define two types of projection. One is orthogonal projection. So we have Pn is the orthogonal projection. It is the best approximation to extend. So Pn usually this is the usual inner product in L2, capital L2. So this Pnx comma some z, but z is extend. So it is the best approximation, and it is an orthogonal projection. This Pn is an orthogonal projection. Let's find another projection, which is called interpolative projection. That means how do you define that projection? We'll choose some point in each subinterval. Those are called collocation points, and we fit a polynomial. So here we have chosen r points in this k interval. So we'll fit a r minus 1 degree polynomial, and define a projection that q, which interpolates on that point, which interpolates x on those points. And this is the relation that x minus that q1x. This is the polynomial q1x is the polynomial in each subinterval in this thing. So we have this Newton divided difference, where this represents the Newton divided difference. So these are the two projections we have defined. Now, projection-based methods, we have classical Galerkin method, collocation method, iterative Galerkin, iterative collocation. Those are also called Sloan method. Okay, Galerkin means when we choose our
projection pi as orthogonal projection, and collocation method when we choose our projection as interpolated projection, QM. And modified projection introduced by Professor Rika Kulkarni. So this is one projection method. It is better than our classical method. Better in the sense it converges faster than our previous solutions like Galectin and iterative Galectin collocation and this thing. In that sense, it is better in the case of kernel and quickly singular kernel like now. And now what we do, we'll discretize this method. Discretization means, of course, projection itself is a discretization. Discrete means we'll use projection and we'll use maelstrom as well. Projection plus maelstrom implies discretization. So why do we need this discretization? So when we compute this solution by these projection methods, so they are integral because of the integral operator k and the definition of orthogonal projection, that inner product that involves integrals. So in the computation for these solutions, we need to evaluate those integrations by some numerical integration like trapezoidal or something. Simpson. So we'll discretize these things. We replace all the integrals by some integration formula, and we'll define our new operator, and we'll show that that operator equation has a solution. So that is what we want to show. So we define it numerical formula. It may be anything, any formula, numerical quadrature formula. So it is 0 to integration. It is replaced by this formula, some numerical formula, and using this definition, we replace this integral operator by this formula, which is the composite one. So this. So k is the integral operator, and using the previous formula, we define this k. That means integral. This integral is replaced by the quadrature formula, and we call it km. Now, what is the disadvantage we have? This km, this operator, it doesn't converge to k. This sequence doesn't converge to k in norm. Operating not operator norm. It converges pointwise. That is one disadvantage. So yeah, but they are collectively compact family. This family is collectively compact. So using those, this collectively compact this thing, using with those, I will show that. So now let's define it inner product, discrete inner product, because so first we have discretized the integration in the operator k, and then we will discretize the integration in the inner product. So we will replace this inner product by integration, and we define a new this thing. Of course, this should not be inner product. This will be semi inner product. So inner product by this rule integration, and we define our projection, which will with this way. If we define this thing where this beta I or the orthogonal basis for xn. So we define a PNX like this, and it will form a projection, and we can prove that for each x in, I mean, if it is continuous function, there is a unique PNX in xn, unique z or say y in xn, so that we can call it PNX, and it will follow this thing, and we have this standard way of this thing. So we are focusing on, let's say, modified projection method. So it is complicated. So this is the operator. This is the main operator, and this is the operator we have k. So k is replaced by km, and this pi is replaced by discrete thing. So we'll show that this has a solution. Okay, we have this as a solution. I will show that this as a solution. So for that, we have defined an operator like this. Using this thing, using is a collectively compact family and this pointwise convergent. where this derivative is called the Fresher derivative. So K is nonlinear. If K is nonlinear, the Fresher derivative of K is linear. So we can talk about its eigenvalue. Of course, as it is compact, K is compact, its Fresher derivative is also compact. So compact, so one, if it is eigenvalue, all the spectral values are the non-zero spectral values are the eigenvalues for a compact operator. So if one is not an eigenvalue, so then I minus k dash phi is invertible. So using that, we can prove that this invertible and this and collectively compact family, we can show that this has a fixed point by fixed point theorem or contraction theorem. So you can prove that this has a fixed point, and prove that this has a fixed point using some analysis, and that fixed point is called, let's say, Zn, and this is the solution. You can see that if something is fixed point, that is satisfy this equation. If Zn is a fixed point, if you put here, we'll get this Zn, this equation here. So yeah, so that means that our discrete equation has a solution. So that, and we have also, so this Zn is the discrete solution, and our exact solution is pi, and this estimate will give us the speed of convergence as well, order of convergence as well. Yeah. So I'm not going to go to the order of convergence part. So only analysis part. So we have used this thing. Yeah, that's all. So these are the differences. So these are the papers on discrete. So on my talk, I have used this. I have taken help from these references. Okay.
Hello, questions from the audience?
How do you check that one is not an eigenvalue of K prime?
Okay, K prime is a compact operator. So okay, that is our assumption. That is our assumption to make. We need to. So we need this to be invertible. I mean, this I minus k plus phi invertible. We need this thing. For that, I minus k dash. That is our assumption. That one is not an eigenvalue category. So
my question is, how do you check whether the assumption is true or false?
So how do you think the assumption is true or false?
Check. What is guarantee that one won't be part of the circle?
See, this k dash is, you are assuming that original operator is not an eigenvalue, right? Yes. So it is the resolvent. This k dash.
Okay. So I is we have, so our k, if k is nonlinear operator, so here we are working on some neighborhood. So it can be proved that this is phi if it is a solution of the x minus our main equation, x minus kx equals to a. If phi is a solution, if it is isolated solution, so then it can be shown that I minus k dash phi it is invertible, and one is not an eigenvalue. From there,
I think Tn is collectively compact to T. One is not. If one is not an eigenvalue of T, then one is not an eigenvalue of Tn for large n, because that is the assumption. One is, but you can say that because Tn converges to T in a non, for instance. And Z is in the resolvent of T, and Z is in the resolvent of Tn for large n. If no questions, we thank the speaker for his talk.
thank you.
Next, I will invite Raj Shidar, a PhD student, and he's a professor from Vivekananda College, to give the talk. His title is Asymptotic Expansions for Approximate Solutions of Boundary Integral Equations.
Good afternoon, everyone, and I thank Department of Mathematics ICT for giving me chance to present in front of you. So, our research topic, title of our research is asymptotic expansion for approximate solution of boundary integral equation. So, here we have a Dirichlet problem for the Laplace equation in polygonal domain. And this problem can be converted into double layer potential formulation, which is also a Fredholm equation of second kind with kernel, as you can see. Now, we have a polygonal domain. We have considered this example where we have 6 corners in this. This is L-shaped polygonal domain, and we have to solve this. But there are challenges that we face. The first challenge is infinite dimension, then singularity at points, and specifically in this case, it's at corner points. Then time complexity, error. The convergence that whatever. So when we are solving infinite dimensional problem, we take a projection and we try to solve it in finite dimension where we approximate the solution. So that time we try to find out better approximation which will give us better convergence. Now what are the solutions for this? So we can use orthogonal projection. In our case, we have used Galerkin method. We can avoid points of singularity, and to compensate for these points of singularity, we use graded mesh where near corners we put extra points which will compensate for that missing point. Then quadrature method. So here we cannot take corner points. So we are considering Gaussian quadrature method where we are considering points around the corners but not the corner. Then choice of operator. What kind of choice operator that we are choosing that will help us to reduce our error. So our work is based on the earlier works. For example, graded mesh, concept of graded mesh is suggested by Rice, and for Galerkin and iterated Galerkin method, we are using results by Chandler, and our paper we are extending work of Roon and Zhou. And also here we are using modified projection method suggested by Dr. Rekha Kulkarni. Our goal is we are going to demonstrate modified projection method. It can enhance the convergence in application based on the work by Roon. So we are, I will just move forward. So we have the domain as I showed you earlier. So we decompose this domain. We make partitions of it. So let's consider there are R partitions in that. Now we have to use different norm. So we define a special norm for this. So you can see in front of you. Now this norm over all the boundary, we can consider this norm, and this norm happens to be so we generate a space which is a Banach space with respect to the defined norm. Now we consider an example. So let's consider this is L-shaped domain, and all the color parts are the partitions that we have made. Now every partition, every corner has left side and right side. So we have now two R parts. So original R partition, and within each partition we have two parts. One is on the one side of the corner and another on another side of the corner. So we represent it by gamma j plus and gamma j minus, and our unknown function u that we consider as u1 to ur, where all the odd ui's are from negative parts, gamma j negative, and all the even parts are from the gamma j positive part. And our kernel, we are defining it like this. So Tj Uj plus, where our S is in the negative parts, and for Tj minus Uj minus, our S is from the gamma j plus part. So by doing this, we get blocks of Tj like this. So this is a one block for a given partition. So like this, we have R blocks, which will give us R by R cross 2R cross 2R system, which can be represented as I plus, on the diagonal we have T1 to TR. The inverse of this, this system is bounded. Now this result is given by the rule. And so we can write our equation as I plus T of U is equal to S. Now we can see that for every partition, this Tj is a bounded function in LP. So there's a mistake. So R can be replaced by P. So in LP it is bounded. So for P tending to infinity, we can show that this under maximum also it is bounded, which gives us bounded inverse I plus T, and with proper regularity conditions on alpha and n, we can show that in a given space, in a given Banach space with that defined norm, I plus T inverse is also bounded. So I mentioned graded meshes. Now here you can see at near every corner we have dense points. So we are trying to compensate for the singularity. Now here we are considering for we are using the Galerkin method, and for that we are considering constant polynomial and orthogonal projection pi h from L2 gamma to SH. Now here pi h, I minus pi h are bounded. So T pi h, pi h t are bounded. All of these are bounded all of these are in max norm, they are bounded. So the inverses are also bounded. Now this is Galerkin approximation of our given equation I plus t, and iterated Galerkin approximation that we can consider UH star, where UH is parameterized by the H1, H2, HR. So we have R partitions. From every partition, we are considering H1. Now HI is T of I minus pi h u is bounded, and the degree of h is 2 in this case. And we use, so there is another proposition which tells us that this operator T I minus pi h u is of order 2, and the asymptotic error that we get is of order 4. The modified operator method, we use modified operator where we consider this T nm as our operator. Now we consider that this UNM is a unique solution for a given equation, and the iterated approximation is given by UNM tilde. So these are our improved results that we got considering regularity conditions. So there is slight changes in the regularity conditions. So here we get, so we are applying, we are using T of I minus pi h over T of I minus pi h. So here we get we get fourth order, and for asymptotic error we get h of sixth order. So error in this case u minus unm is of order 3, and iterated approximation error is of order 6. And the error analysis. So this is error of order 6 that we can see. So this result which is given above is by root, and the improved result that we have proposed is below. Now, future work that we are working on the numerical analysis of all these theoretical findings, and we are trying to check whether can we change the refine our mesh, and can we use higher order basis as our functions, and we can also investigate non-linear problems as well. So these are the references. These are acknowledgements I would like to mention. Thank you, everyone.
Questions? Let us thank the speaker for this talk.
Thank you.
Thank you to all our speakers for the engaging and thought-provoking talks, and a special thanks to Dr. S.I.W. for chairing both sessions, session 1A and 1B, so gracefully. We now break for lunch. Kindly proceed to the Godrej canteen ground floor for lunch. The volunteers will assist you. The next session will resume sharp at 2:30 p.m. Thank you.
इसको बंद करना Prefer to stand here, right?
No, I actually want to move. If
Okay,
that's
yeah,
not a problem.
I'll keep it like that so that at least you feel.
Okay. Some portion of my body is visible.
Yeah.
If I don't want it to be visible. Say I start, I will start. I don't get it.
थोड़ा बैठ जब स्टार्ट होगा ना तब एडजस्ट करके
स्टार्ट करूंगा अच्छा
Welcome back, everyone. We now resume with the afternoon technical. Welcome back, everyone. We now resume with the afternoon session of day 1, session 1C, themed around topological data analysis and machine learning. This session brings together thought leaders who work at the fascinating interface of geometry, statistics, and AI. It is my pleasure to invite the chair for this session, Dr. S.I.W.S from IIT Bombay, to conduct and guide the session. Dr. S.I.W. is an assistant professor in the Department of Mathematics at IIT Bombay. His research interests include time series analysis, non-parametric regression, and high-dimensional data analysis. Please welcome Dr. S.I.W.
So probably I don't need this. So welcome to this session. Dr. Thirumalai, this one day is from CMI, and his interest is in algebraic topology and combinatorics. He will be talking about introduction to topological machine learning.
Okay. Thank you for the invitation. It was great to meet my friend after 2 decades. Very good. Okay. Right. So, okay, what is this talk about? Right. So, I want to start with. So I'll start with background. Okay, so let me give you a pre-introduction. So topological data analysis grew up maybe between 15 to 20 years ago. And the basic idea is that you look at data not just as a set of isolated points in a vector space or a metric space, but you sort of assume that it is sampled from some shape. And you want to understand this shape in some way. And algebraic topology offers you tools, techniques, and in particular vocabulary to describe these shapes. So initial efforts were mainly about quantifying this vocabulary and techniques. But later on, maybe 6-7 years ago, people also started putting these quantifiers in a way so that it will serve as an input to machine learning algorithms. And the trend has emerged in last, let's say, from COVID time onwards to actually bring it into deep learning. So I'll not touch on that. So unfortunately, I'm not going to talk about this introduction to topological data analysis, but I'll go one step further in how things are used in machine learning. I'll try to give you an intuitive picture and I'll end with an example. So as I said, the motto in this field is data has shape and shape has meaning. Okay? So you don't look at data just as a set of isolated points, but you assume that they are sampled from a shape, so it should have been encoded. So actually a topological space, it doesn't matter if you don't know what a topological space is for this talk, you think of its shape because it really matters if you have done some data analysis like fitting a straight line, right? The basic first example that we all see. But for that, you want your data to be more or less linear. It should be sampled from something linear. Then the best fit makes sense, right?
If you have only two variables, then you can visualize, and just by looking at the scatter plot, you can sort of judge, oh, maybe a line will not fit, a degree to curve may fit. But imagine that you have data which has, let's say, 10,000 coordinates, and you have some 10 lakh points. Then there's no way you'll be able to visualize it. So then, what sort of shape technique are you going to use? One, because you don't know what you cannot guess what the shape looks like. And the second is, you don't have vocabulary. Like, how are we going to describe a shape? Right? We don't have those. So, for example, in 2 dimensions, we have surfaces. So there are some invariants that completely classify 2-dimensional objects. So we have more or less understanding in dimensions 2, more or less in dimensions 3, but 4 onwards, it's even theoretically impossible. So you don't have vocabulary to express shapes, and then we cannot expect to have a shape-dependent cottage industry that, okay, if I have this shape, then I'll use this analysis technique. Right? So we want some technique which will sort of internally understand what the shape is somehow and adapt itself accordingly. And that's exactly where algebraic topology comes to help. So traditional machine learning focuses on statistical patterns. Topology looks at coarse scale global geometric features. So for example, in 2 dimensions, you want to say, oh, a part of my data is sampled from an annulus, or it has a central core, some flares are coming out of it, something like this, right? You want to have vocabulary even in high dimensions. And the key assumption that people put is that if you have some insight into the shape of the data, it yields insight into data itself, right? So what's the role of topology in this? As I was talking earlier, it sort of gives you sort of an array of techniques which remain unchanged under the continuous deformations. These techniques are independent of how data is presented to you, the choice of coordinates, the choice of embedding. You don't need to. So, I mean, the intuitive example that I usually give is, suppose you have a circle in 3 dimensions, and then you are looking at it at eye level, so that the sort of middle pole is not visible, and you may mistake it for just a line segment, because the way we are looking at it, we don't know that there's something. It goes around and middle portion is one. So that is because of the choice of coordinates and embedding. So we want techniques which are independent of all these, and algebraic topology offers these things. Some of the salient features are all the topological techniques, either in data analysis or machine learning, are proven to be robust when it comes to Swann perturbations. I'll give you some information about this. And again, these are regardless of how data is presented to us. And at least from shape point of view, there's a lot of interpretability, there's a lot of explanations that we can give. So one such technique in topological data analysis that I'm going to focus for today is this persistent homology. So, first of all, what is homology? So homology is something people usually learn in the first course of algebraic topology. To put it very intuitively, it's a hole detection formalism. So one aspect, one of the vocabulary to describe shapes could be how many holes of various dimensions it has. Right? So all of this can be made very precise and extremely formal. So by a hole, you have to understand a copy of an I-dimensional sphere is called an I-dimensional hole, and 0-dimensional hole is basically just connected components. Then you have points. So then you have 1-dimensional hole are basically embedded circles. So it could be simple closed curve or so this is just an intuitive idea of what homology captures. So persistent homology actually computes. Okay, so maybe it's better I show with an example right here. Okay, so here you see that I have some data. This is a very toy example here. So just by looking at these points, we can sort of infer that these points are sampled from 2 circles which are possibly connected at a point or some portion of their circumference. Now, what I'm going to do is, in order to understand that, in order to guess that these are actually sampled from circles, I'm going to keep drawing discs of increasing radii with these points as centers. And then I'm going to look at these shape. Right? So initially, when the radius was 0, I had these discrete points. So whatever the number is, I forgot, maybe some 12, 13. So I have 12, 13 different connected components. Then I keep increasing the radii, and for a while, none of these disks intersect. So for all that, so this is the radius parameter that changes, and these y-axis is keeping track of topological features or shape features. So here the first shape feature is how many connected components that shape has. So initially it has whatever the number of connected components is equal to the number of points. Then it radius starts growing, and at some point some of the disks intersect. So reducing the number of connected components, which is reflected here because these horizontal bars stop growing, indicating that that particular topological feature is no more. So there was a connected component for, let's say, from 0 to 0.6, but 0.6 onwards it's not there. Then we keep increasing. Then at certain point, all these disks intersect. So you get a single connected component, but at the same time, these two holes have emerged. And that's the first homology, which is being detected at this level. So at this radii, maybe this radius parameter, this small circle was formed. Later, this big circle came up, and the radius keeps increasing, and this circle is now gone, replaced with a connected component. This hole is gone, so this bar terminates here because at that radius the hole is no more, but this hole is still surviving. Then it keeps increasing, and at some bigger radius, obviously everything is now just a blob, right? Which is union of this, and so this bar also ends here. So this is keeping track of these topological features, namely connected components and holes, at which radius parameter a particular hole was born, was it alive, and then died. So these are my barcodes because they look like barcodes. And they keep track. This is the radius parameter, this is the individual topological feature, and keeps track of how long a particular topological feature was alive. There is another way of representing it, this equivalently. You take bar, so it has a starting point, called this birth of the feature, ending point, one is the death of the feature, and then death is always bigger than birth. So when you plot it as birth comma death, you always get a point above y equal to x-axis. And this always starts with 0 because at radius 0, you have disconnected, like isolated points. So it always starts with 0. Now, how to interpret this? Okay, so there's a lot of theory behind this, which I'm just completely sweeping under the rug. But what it basically says is that the bars that are of longer length, which means the topological features that persist for a long time. I mean, it's all in relative sense of this radius, are the prominent features of the shape from which the points were sampled from. So if I were to look at this, what do I see? I see a red dot which is very close from the origin. So it means that the prominent feature of the shape underlying the data is that it's a connected shape. There are two blue dots isolated prominently away from the diagonal. So it's connected and it has two holes. That's what I read from here. The shape from which the data is sampled. So you can formalize all this. There's a lifetime of a cycle. So the topological feature, the formal name of topological feature in homology is called a cycle, but let's not worry about this. So these pictures here themselves actually form a matrix, because I'll show you how. So that's very good. The points are grouped by scale similarity that's stable with respect to perturbation of the data. That's also I'll show you. It's sensitive to sort of small and big holes defined appropriately. It's possible to track, record the size, scale of these features, and it's not sensitive to outliers, and it's computable in practice. So there are very good efficient algorithms available that will do it for you, starting from so your input is data, that these algorithms which will do this, and your output is this. Okay, I'll show you. Okay, so here is an example that I did. So all of us know the surface of the torus, right? User here on the top. And so what I've done is I've taken the equation, one of the equations of the circle, the torus that sits inside R3, just sampled 300 random points that satisfy the equation, do this kind of thing. At the end, you get this barcode. Now, if you look at the features that are away from the diagonal, so this is one, which says that it has one connected component. This is one dimensional, so it says it has two one-dimensional holes, and this says it has one two-dimensional hole, which are exactly the Betti numbers of the torus, if you've seen this, but this is pretty much what we understand from the surface of a tube or a donut or a wavelet or whatever you call, because it's connected. It has two holes, longitudinal and meridional, and there is nothing inside the surface, right? It's void. So it has one two-dimensional. That's what this persistent diagram captures. Okay. So now we could actually define distances between, sorry, this one actually, these kind of diagrams. So basically, if you have different data on every data, I'm doing this persistent homology calculation, I get this as an output, then what do I do? So you actually compare. You can define various long distances called Weissenstein distance, depending on how you do it. But again, let me give you a pictorial or a visual thing. It's called optimal transport distance. So basically, you will come up with all possible bijections, and every time you will measure the distance using a particular norm, and then take the supremum as you run. Supremum of this and infimum over all the bijections that you run through. And this is again computable. Almost all the Python, R, Julia packages have bottleneck distances implemented. But again, this is not the point of the talk. This is the most important thing I was saying. So if you have two point cloud data, right? So if you have two point sets in any dimension, doesn't matter, in any vector space. So the output is the persistent diagram corresponding to persistent homology. Then this bottleneck distance is bounded above by the Hausdorff distance between these two data considered as closed sets. So if you change a little bit here, not much is going to change here. So this is what I mean by this is agnostic to perturbations. And again, there are a lot of tutorials available online. You can also do it by yourself and actually check, verify that this is in fact true. And this also has a proof. So, the main issue people thought was, okay, this is a good tool for visualization. We can understand, but I should be able to do some statistics on these persistent diagrams. And that's the problem. It's not very easy because, I mean, basically, this, can you consider persistent diagrams? Can they behave like a random variable? No, that doesn't really happen because of one of these problems that the Freshet mean is never unique. So that lands into a problem, but not a problem. There are ways around this, and this is the main theme of today's talk. That this output, persistent diagram, it sort of tells you about the underlying shape of the data, shape of the underlying shape of your data is that there are various methods that will convert your persistent diagram into a couple of real numbers, a vector, and you can actually use it for machine learning. And I'll show you one example. So this is a typical pipeline for topological machine learning. You have data, which could be a point cloud, a time series, an actual 3D shape, or a complex network. Somehow you have to come up with a way to build a shape on top of it. So I showed you one way of, if your data is in vector spaces, then you can have these disks of very increasing radii. So that's one way to make your discrete data in continuous form. It could be other ways. So there are various like check, victorious set, sub-level set. It could depend on context, not a problem. Then you run this persistent homology, whose output is these barcodes or persistent diagrams, doesn't matter, either of them, both of them. Then you vectorize these topological signatures or topological descriptors, and then these vectors become input to your machine learning technique. So I'm going to, for the purpose of this talk, I'm going to stick to only classification tasks. Okay, so the first is landscape. So 10 minutes. Okay, so let's get rid of the background. Okay, so what is landscape? So you have a barcode here. So you look at a particular bar, you convert it into this triangle using this very simple function. Okay? So you get this peak function for each persistent cycle. And then you look at maxes. So if you have 3 bars, your output is this outer thing that looks like a landscape. So you get a vector in this particular Banach space. And usually, so let me show you, this is usually how it looks like. So usually, if there are a lot of bars, or if there are a lot of long bars, people usually just take the norm of each vector. So you get actually just one real number and work with it. But this one real number is extremely useful. For example, there's a stability theorem again for landscapes. So these landscape vectors, so suppose you have 2 data sets, x and x prime, then the bottleneck distance gives you an upper bound for the difference between the absolute values of these landscape vectors, the difference between the landscape vectors. So it's also very stable with respect to perturbation. So if you do a little bit perturbation in your data, there are outliers, this output doesn't really matter. You also have a mean and other good things. Yeah, you can also define the norm of your persistent diagram using landscapes. That's very useful. And again, this computable, almost all the Python, all the PDA libraries available either in Python or Julia have this implemented. It's very useful. The second vectorization method, which I think is a real number, is called entropy. So it's just like your information entropy, but instead of information, you look at lengths of bars and you try to compute entropy there. Then you also have a Betty curve. Okay, here is a better picture. So basically, it tells you at a sort of given value how many bars there are on top of it. It gives you a piecewise linear function, and that's your vector. This one is more interesting, and this is also being implemented. So this is a sort of a variant of something called as kernel method. So before lunch, kernels were introduced several times. So this is exactly those kernels. So the idea is okay. So each point you associate a Gaussian, and then you get a surface. Okay, let me show you how it works in practice. Okay. So for each point UV in the persistent diagram, uh, this is the Gaussian distribution that you associate to it. Now we found this persistent surface from this distribution, and then you calculate this integral, double integral, and sorry, I should have. So this is what the surface is. So it's like a heat map, and then you pixelate it, so you get an image. But image is nothing but a matrix. So the values here is your vector. So this matrix itself becomes a vector. And amazingly, I mean, it has a really good theoretical properties. And though the definition looks pretty complicated, non-obvious, but in practice, the results are just amazing. And persistence image. Now this person image will be input to the machine learning or a classification task. All right. So now, yeah. So there are other approaches as well. For time, I'm not going to talk about this. Before kernel methods, I want to show you one example. So before that, let me explain to you what the classification task is. So this is image classification. So there is a very famous data set which is called endless handwritten digits data set. Maybe some of you know this. So it's a collection of maybe like 70,000 28 by 28 black and white images of digits 0 to 9, and people have written those digits and you have pictures. And it's available. In fact, it comes for free with many like Scikit has this, or you can just go to the Endless website and download it. Yeah, now it's like universal available. And anytime you write something classification, the first thing is to check how it works against this data. So this is the thing. So I have sort of 10 classes, 0 to 9, and total 70,000 images. And I want to build a topological machine learning pipeline. So each image is now treated as data. Right? It's 28 by 28. So usually what people do is they convert this image into a vector by just expanding it in around rows and get a vector of dimension 756, 786, whatever. And then work with it. So instead, we're going to look at each image as a shape, right? And then see what happens. Right? So I'm again going to do some magic, and I'll directly show you what the output is. So every time I'm going to do some different way of filtering it, which means building a shape on top of this data, and I'm going to use all the vectorization methods. And then we basically ran classification, and I took a two-dimensional projection of the final classification. And this is the output I want to show you, because there are a lot of things that so I will share, right? So stop sharing this and share something else. Where did it go? Oh, sorry. Yeah. Absolutely okay for this. So this should go up. Okay. So what you see in front of you are the end result after classification, and I've annotated it using the thumbnails of the original images. So there are, I mean, you don't have to count, but just trust me that there are 10 different colors, each representing a digit. So let me show you. So this is a cluster of all ones, but it's not just sort of an arbitrary cluster. So I'll go slowly. look at the ones here. Okay? Just keep track of what you see. And as I move to one end, so if you remember, the ones here are very thick. The ones here are very slim. Right? So look at the ones here. They are nearly straight and very thin. Right? So this is like a shape, inherent shape property. Right? So let me show you the inner ones. So all these are 6. Right? Again, there is this sort of thick 6s, thin 6s. Right? Now look at the 6s that are here. So these are, now this turns into 8s or 9s. So these are 8s. Again, so there are of course some misclassification, but this is like some 97-ish% accuracy. But of course there are some misclassifications, I have no idea why. But okay, so there was some interesting, yeah. But there is also one cluster of 8s somewhere. Look at the 8s here. So these are 8s, but the second group is not complete. So those are also separated. Then there are, okay, so 2s. Look at these 2s. And look at the 2s that are here. Of course, again, you'll see that there is misclassification. Some of the 7s are here. But so the 2s that are here do not have a loop, but the 2s that are here actually has this central loop. So this, if your data has some sort of intrinsic shape, it finely captures it. And this is just a simple example, but people have used it in various contexts. Anirvanta in a morning talked about stock markets, but there are other applications also. But I thought this would be easier to explain, and this you can actually formalize. It's not at all. Yeah, so maybe in last 1 minute or so, I could just briefly mention. See, persistent diagrams are not vectors. So there is another way of vectorizing them by putting this inside a Hilbert space, something known as a kernel, which was introduced before lunch. So I thought, since I also have it in my talk, I'll just show you. They're also used. So basically, it's just interested in these positive definite kernels. So you have some set, doesn't matter which one. Basically, you need a function which is real value, 2-variable function which is real value, symmetric, and for any finitely many points, this k of xi xt, the gram matrix, has to be positive semi-definite. So, for example, if omega is Rn, you can just have inner product. It satisfies all this. So it's a positive definite kernel, but you can actually do it for non-vector data or non-vector sets also. You form something called as a reproducing kernel Hilbert space. Again, so one of the things that is implemented in Python libraries is this Reinhouse, the paper which came out 6 years ago. This kernel has been implemented. So this is a persistent diagram. This is another persistent diagram, and this is the kernel. Again, it has some underlying statistical theory behind it. Why to choose this? I'm not going to go into that. But you get these real value. Yeah, so you get these real numbers, and this is what is used as an input to. Thank you. Questions? Sure.
You went from data sets to persistent diagrams to data sets.
Or vectors.
Okay.
Yes, yes.
And you were measuring stability in terms of the Hausdorff.
Yes.
So where in the Hausdorff?
Yeah.
Does the vector norm also come into, is that a better way to move to
No, so the Wasserstein metric is on persistent diagrams, right? So that diagram is, a subset of first quadrant, which is about y equal to x, right? So what is important there is their sort of relative distances from each other and from that y equal to x line. Because the farther you are from y equal to x line, the robust that topological feature is. Anything which is close to the y equal to x line are short-lived, spurious topological features which one should discard. So the best distance there is the Wasserstein distance, or the Wasserstein optimal transfer, right? So that's the distance there. So that is the distance on persistent diagrams. Now, what is going to change that? If you change something in your data, the persistent diagram will change accordingly. What stability theorem says is that how do you measure changes between 2 point sets? That is using Hausdorff distance, because these are closed subsets, right? So you want to, what is the, how much, so I have original data, it's slightly perturbed. So what is the Hausdorff distance between these 2 point clouds? Now that becomes upper bound for the perturbed, for the persistent diagrams of the perturbed data. So that's why. So what it says is that small changes in your data points will not affect the output of the persistent. Persistent diagram.
The persistent diagram.
No, so we have to I mean, you cannot ignore that because vectorization is of the persistent diagram.
So there is no way of vectorization is also insensitive to perturbation.
Yes.
And that's your usual norm of indexes are.
Yeah. So, for example, landscapes were in particular Banach space. So you use a norm vector there. But if you go for entropy, entropy is just a real number. So then you just do the usual subtraction.
Already takes care of all the matchings that you have. So
Yes. Yes.
After that, you need to sample from compact.
No. So when we do this, compact, non-compact is not even relevant. Yeah. Except for that image, I mean, the torus thing was just a toy example. I mean, see, the idea here is not even get into algebraic topology. We don't even want to know. We just want these topological descriptors. And okay, so one thing I should confess, TDA or TML is not a standalone technique. It's not like you know about shape, it's going to solve all your problems. Except for that image thing, which happened to be like a shape in itself. Everywhere else, TDA is going to be supplementing your other quantifiers.
So you show those pixel are you using some information?
No, so that is my vector. I feed that to the classification.
So CNN.
Yeah, wherever you want. So I'm going to use that matrix as my vector and use it. Yeah. In fact, the classification that we did for images was done using persistence images.
Yeah, so I was just curious, what exactly are those persistent diagrams mentioned? Like one thing you mentioned, there was some ECC that the petty numbers are there. But like in those numbers, for example, if they have the same homology, it's like the thick one and the thin one.
Yeah, good point. So, okay, so it's slightly more subtle than Betty numbers. These are, so these are something, so there is no sort of consent name for this, but I would like to call this filtered topological invariance. So you have a topological space, then you say, oh, they have two. So for example, 1 and 3 considered as shapes, right? How you draw 1 and 3, usually, you look at Hutcher's book, they'll say, oh, digits 1 and 3 have the same homotopy length. Agreed. But if I look at various filtrations of 1 and various filtrations of 3, there is a difference, and that's what this captures. So You have to have, suppose I had done only one filtration technique, I would not have gotten these many differences. So as I said, I put everything under the rug. But the thing is, see, okay, let me give you one. So try to visualize this. You have 5 and you have 7, right? So if you unravel 5 as a shape from top to bottom, the way it looks at every stage is very different from 7. Same thing if you go from right to left. Topological features are different. So you try to filter your shape using as many techniques as possible. And for each filtration, you compute a persistent diagram. For each persistent diagram, you vectorize it in some way, and then you pad all these vectors together. So that's sort of the.
Last question.
So,
Yeah, first of all, nice talk. And this is first time I'm sitting in heard about topological data science and all that, etc. So I mean, my question is non-technical. See now we are teaching topology, algebraic topology, homological algebraic topology. So it may be nice, good idea to kind of building some of these examples in the regular course so that they otherwise it becomes quite disconnected. And
no, I totally agree.
Yeah.
So people have tried this. There are recent years sort of short courses on TDA for people with no background in algebraic topology, or people have also tried to include these in their teaching. So yeah, I think slowly we'll have a more comprehensive material that will connect to what we have. So currently there is a book called Elementary Applied Topology, which covers a lot of things where topology used in non-theoretical settings. But it's a bit too comprehensive. So it's like a handbook of all collections. So maybe you can choose, you can choose. Yeah. Thank you.
We have a moving to presentation of you. Yeah.
I request Chai to kindly present the token of appreciation to the speaker.
Okay, some meme. Oh. So, I have a very long voice. Our next speaker is S.I.W.S. He's from CMI, and his research interest is in Bayesian statistics, machine learning, and big data. So, over to he will be talking about Jacobi triad and alternative Bayesian method for supervised learning.
Yeah. So, thank you and giving this opportunity to is it clear? Yes. Okay. So I keep coming to Mumbai. And after and I always had a hope to visit ICT and able to visit. So let me start my presentation. So this is a joint work with my PhD student, Big Shota. So as usual, PhD student does all hard work, and being faculty, I'm making the credit here. So let me tell you what is supervised learning in machine learning. In machine learning, there are okay, sorry. So In machine learning, there are few areas. One is supervised learning, another is unsupervised learning, and there is an area called reinforcement learning. So probably the most well researched, understood area is supervised learning so far, and so it is a bit difficult to really have a tap on some coming up something new in this area, but still be able to manage to do that. But let me give you what kind of problems actually falls in supervised learning. So, for example, you applied for a home loan, right? I'm a bank manager. I have to, if I give you the loan, and if you return the loan with interest in regular EMI and all the up to 10 years, bank make good money, I get a promotion. But if you fail to return the EMI on time, bank NPA goes up, I get a demotion. Or I get a transfer to a very bad place where I don't want to go. So this is the kind of problems which falls. Basically, as a bank manager, my job is looking at your job, looking at your salary slip, looking at your income tax return, looking at your educational level, what kind of job you can do. All this information, I want to judge whether you will be able to return the loan on time, you will be able to pay your EMIs every day. So I have to predict. Okay. So this is one example. Now there are thousands of such examples. Another example is I am running a shop. I want to figure out, okay, I'm selling bread. Should I price the bread at 50 rupees or should I price the bread at 45 rupees? Because if I increase the price, am I going to sell 2 units of less bread? Right? So again, it's a prediction. So it's a classical demand supply prediction problem. So any kind of prediction problems you can wrap up into the area of supervised learning. And in that supervised area, there are you can do many things. You can do deep learning neural network. You can do classical statistical modeling. So we have taken classical statistical models and developed a Bayesian method for that. So here is the introduction, motivation, then why it probably requires some simulation study and some empirical study. Then discussion is all. So I have taken something called generalized linear model setup, very standard setup, 1980s model, very standard. Y is the dependent variable. It has its coming from a distribution. It could be Barnum distribution, it could be Poisson distribution, it could be Gaussian distribution. You decide some proper probability distribution. And then it has its own parameter theta. It could be proportion, the probability. It could be rate parameter if you are Poisson assuming, also if you are assuming normal, it could be mean. So depending on your problem statement. Now, not necessarily these parameters will be on the real line. You can have a restricted parameter space. So if you are working with Bernoulli, your parameter is P is only between 0 and 1. So you cannot work with it. So we need some kind of transformation. We call it link function. Okay. So once we put that, we get the eta I. Eta I, it's typically G, the link function is a one-to-one function, so that we get something on the left side, which is on the real line. And then you have a bunch of features or the predictor variable, which will help you to get the model set up. Now, the problem that I told you, whether I have to give you the loan or not, in that case, your y will be like 0 or 1. 1 means you will not be able to pay back the loan, 0 means you will be able to pay back the loan. X will be like all kind of your predictor variables, like your income statement, your educational level, all whatever they will So if you know the beta, then all the activities I have to do, get all your information, plug that, and that will give me the theta. Theta is in this case P, which is expectation of y will be P, and I will know if the P is very high, that means chance of default is high. I will not extend the loan. If the P is low, I know that the chance of default is low. I will take the chance, I will review the loan. So this is, so only thing I need to know is beta. I don't know what is beta. So in statistics, we call it estimation problem. In machine learning, we call it learning problem. So basically, I don't know beta, I want to learn about beta. This is all we have to do. Now, what we do, we generally define a likelihood function, straightforward likelihood function. We define it in this way. And then, in a Bayesian setup, what we generally do, we generally assume a probability distribution on beta, and then we apply Bayes theorem on that. That gives you a posterior distribution of beta. Now, knowing the posterior distribution is not enough, because it tells me, okay, here is the possible region the beta could be, but that's not very useful. But what we need, I need an estimation of beta. So what I need to calculate the posterior mean, which is integration beta posterior density times beta. If you integrate out the beta, you will get something estimated. It will be function of y and x. That's called Bayes estimator. So posterior mean will be a nice Bayes estimator for beta. Or you can do a posterior mode. That okay, here is the posterior distribution. If I can find the beta where the posterior density is highest, I would prefer that beta value as my estimate. So for that, all you have to figure out where is the maximum of the posterior density. So that is my posterior mode. So now problem is, if you go back, I have p many parameters. So when I will try to solve this integration, it's a p-dimensional integration. So I have to, if I want to calculate posterior mean, I have to solve a p-dimensional integration problem. Or if I try to solve it as an optimization problem, it's a p-dimensional optimization problem. Okay. So this is where the whole process boils down to. So if you want to solve a posterior mean, generally what people resort to, we resort to the Markov chain Monte Carlo simulation algorithms, which is very good in solving a high dimensional integration problem. 220 dimension does pretty flawlessly from this. It's given the computing system that we have. And posterior mode, if you want to do a standard posterior. So these are also very high degree of, very high strong optimization tools that we develop. So that can be solved. So now you can tell me, well, it is a well understood problem. We can solve it. What's so great about it? Now my question is, can we avoid whatever you do, this p-dimensional, either solving optimization or integration, whatever you do, can we avoid this altogether if we have a complete analytical solution? In this paper, we are proposing a complete analytical solution for beta. If we have a complete analytical solution for beta, then you don't have to resort to any of the optimization or integration, so numerical optimization or numerical integration. This is precisely what we aim to do. Okay? So that is where comes the Jacobian graph. Now this is what happens in typical Bayesian setup, people apply prior on directly beta. You take any literature till our, they will directly apply prior on beta. And those, our point is that's very difficult. It's extremely difficult. Instead, you should apply prior on theta. You will have much better understanding where your proportion of default is, or where is the rate of accident, right? If lambda is your parameter, the rate is your parameter, you will have some sense, some historical experience that, okay, where is the rate of accident? So instead of putting prior on beta, what we are saying that you put a prior on theta, okay? So the idea, if you put a prior on theta, then you get a posterior density here, and then you see theta is a function of eta. So I can use a Jacobi method to get the posterior density of eta. Once I get the posterior density of eta, then, or prior density of eta, whatever you call it, then we say that a simple beta x transpose x inverse x transpose eta will be your will induce eta. If you have a prior on eta, that will induce a prior on beta. And similarly, if you have a posterior on eta, that will induce a posterior on beta. So by inducing prior on theta, you are not violating the basic principle of Bayesian data analysis. Because in the Bayesian data analysis, you do your analysis by inducing prior on the target parameter. Your target parameter is beta. So these two theorem tells you that if you actually, instead of inducing prior on your target parameter, if you induce prior on something different, and then use the mathematical relationship to induce the prior on your target parameter, you are still on the Bayesian framework without violating the principles of Bayesian data analysis. Yeah. Because it's a just three-dimensional object. So if I will have a much more sense that, okay, what is my default rate? But if I ask somebody, okay, if my education level is this, then what is the beta? What would be the expected beta that will affect my, my default rate? Nobody has known. Basically, nobody has known. Okay, and also when you are putting a prior distribution of beta, that's a three-dimensional probability distribution. Even in going beyond two-dimensional distribution, is probability distribution is handling is very difficult. We just cannot visualize. Whereas an three-dimensional probability distribution is just not too complicated. People will either put some kind of Gaussian or Laplace with popular, that's it. People will stop here. Or some kind of popular distribution. But it's very difficult to model three-dimensional probability distribution. So with that, we propose that, okay, if you get the posterior estimate here, basically, if you know the posterior density, this is the univariate density. So what we say that, okay, eta hat, it can compute the posterior mode of the eta. It's just solving a univariate function, simple one, just maximizing that posterior density, and then use that, plug it in here, and what you will get is this estimator for beta. So that's what, because we are using Jacobi technique to induce prior on beta, so and to get this estimator, so we are calling it Jacobi prior. Nothing no log loss for this check. So we first thing we did a simple logistic regression, and we did a mathematics and just jumping to the all the mathematical just algebra, the derivation. But you can literally show that data hat can be written in this format, like a OLS solution, like ordinary least square solution. So far, we were only knew for simple linear regression, ordinary least square solution was available. For the other models, there were no solution were not available. They were always either you rely on Fisher scoring method or some kind of gradient descent or stochastic gradient descent, some kind of gradient descent method, you have Newton-Raphson method you have to rely on. My solution is cut across, you have a plugin estimate. Similarly, we have done it for the Poisson regression. Again, we have given a complete analytical form for Poisson regression. And then, so this was first done in Darshan Day 2006. Negative binomial regression was also done. 2008 was done Pareto regression, which goes beyond conjugate family. Al-Dawari Sultan 2021 developed a model for Weibull regression using the Jacobian technique. And then what we did in this paper, we took the TD25, 2015. They developed a distributed multinomial logistic regression for K-class classification, which can be done for very large data sets. So we just thought, okay, we can develop a estimator for K-class classification, multinomial logistic regression also. So we developed for that. And also in this paper, we developed a Jacobi solution for Gaussian process classification as well. So because of the time, I am skipping all those Gaussian process classification thing. So what I did, the first thing I did is let us check out our results, how good they are. So we set up this simulation study where we have taken this beta. Now, why we taken this beta? Because the seminal paper by Picciani in 1996, where he proposed his lasso method or the L1 penalization method, these are the numbers he used. So we thought we will just benchmark ourselves against the seminal paper because we really wanted to push the boundary. Then these numbers later used by Zhao and Hesky in the elastic net also. So series of papers, some reason using these numbers started actually by 1996. Why he chose these numbers, I don't know. Then I need a metric. So we decided, okay, we will go for root mean square error. Now, typically for classification, you go for the accuracy. But after discussion with many of my colleagues, we decided on root mean square error. Why? Because if you see, there could be a model where for a classification, if you rely on the accuracy, what happens if p equal to 0.52, it will be classified as a 1. And p equal to 0.9, it will classify as a 1. Or and p equal to 0.48, it will classify as a 0 because typically it is greater than half, you classify as a 1, and it is for less than half, you classify as a 0. So the accuracy is not really capturing the strength of the p. Whereas I know the true value is 1 or 0. So if my p is close to 1, that means I am really good. So I can have two models, exact same classification, accuracy. But one model is giving me a accurate prediction with 1 as with a 0.7, and another model giving me the same prediction as 1 but with probability 0.9. So obviously the one which is giving me probability with 0.9 is giving you much better accuracy. So this was the motivation. We thought, okay, we will take the root mean square error. We given a very detailed explanation why we in the paper why we chose this. So then, what we did, we over 500 replicate 500 data set was simulated, each of size 100, and model was fitted, and then a test data was generated. In the test data, we calculated the out of the sample accuracy for both in Y as well as in the paper. So what we are seeing in the predictive accuracy, MLE is 0.69, reach, lasso, and elastic net is hovering around 0.66. Horseshoe, it was a prior was developed by Carlos Carvalho and legendary Professor Nick Paulson from University of Chicago, very strong group of Chicago people. So their method is doing 0.68, and our method is giving us far better accuracy in profit and logic, both cases 0.55. Now, all results are not that good. When it is come to estimation, still lasso elastic horseshoe is doing slightly better than our methods. Okay, so it means remember that in terms of prediction accuracy, we do much better. But in terms of inference, these methods still have some value. Now comes an interesting part which is typically statistics community people don't pay much attention, is the time to compute the compute. If you look into the MLE or all these things, if you take the Jacobi logic, if it takes 1 unit to compute 1 second to compute the Jacobi, the MLE takes 18 seconds, lasso reach takes 210 seconds, and horseshoe prior takes 50,000 plus seconds because it relies effectively on Markov chain multi-color method. Now, I'll just take a pause why it is so important. Particularly after COVID, what happens is in industry, particularly, all the computation has been pushed to cloud. Basically, what is cloud? Cloud is big machine on rent. If your computation is running, you have to pay. If your computation stops, you log out from your machine, you don't have to pay. Right now, imagine instead of seconds, for each second you pay $1. So literally, you are paying $1 for Jacobi prior to estimate, and $200 for any regional elastic net, which is a Stanford group, and the Horseshoe price the Chicago group. So we really benchmark against them. So this was with the logistic regression. How much time we have? So similar thing we did for the Poisson regression with count data, and similar kind of results we are getting. So 1.33 here, 1.21 root mean square error, and Jacobi prior was giving us 1.17. So predictive accuracy is better, and in terms of time, because it's an analytical solution, you are not relying on numerical optimization or numerical integration. Now, so this was the multinomial K-class multinomial logistic regression. So in this case, what we have done, we have taken K equal to 4. Basically, it is a 4-class classification, and we took P equal to 3 features because we cannot really just computational time to save. And then we simulated 100 data sets. And we induced about 50% sparsity in the solution space. And this one, what we did, we said that okay, when we are simulating the data, we will not specify any values. We will simulate the true values from the normal zero. So this was what we set up, and then yeah, and then what we found when we did a full multinomial regression, no parallelization, nothing, full multinomial regression. The elastic net regions are all hovering around 0.72, and when we did a distributed multinomial regression, still they are hovering around that, and Jacobi pair is at 0.62. So almost 15% predictive accuracy gain you can see, and the time complexity is like 900 times faster and stuff like that. It's really, really fast. So just completely ignoring the entire numerical optimization, numerical integration process. Then we looked into the empirical study. So there are two, in the paper, there are two empirical studies we have taken. But this one is a 3-class classification problem that we have taken, where basically we have taken the Sloan digital sky survey data set, where we have about 100,000 observations. Each observations are labeled as either galaxy or quasar or star. Okay? It is being labeled and you have to predict the level, which level it is. So basically 3-class classification problem. Obviously it's not image. Image was taken and then they have developed their own way to label it as a either of the three name, and you have to just predict the name. And some of the features or the predictors that we have, alpha, delta, these are all kind of filters in the telescope. Okay, so right acceleration angle, declination angle, ultraviolet filter, basically filters the ultraviolet light, weak filter, red filter, near infrared filter, and infrared filter. So 7 features are given, and then based on using for each observation, you have these 7 features and the level, whether it's a galaxy, quasar, or star. And then using these 7 features, you have to predict whether that observation is galaxy, quasar, or star. So we did some basic visualization, and what we realized that the data is anything far from the Gaussian, or generally very weird kind of relationship we have seen. I never see this kind of thing. So basically, there are 3 colors. Color codings are the galaxy, quasar, or star, and then so for example, in this X is the alpha right acceleration angle, Y is the infrared filter, and the color of the point is the label of the observations. And it's very weird, except this one. I mean, this observation, this one is not particularly. So majority are the galaxy in the data, almost 70%, and about 15%, 15% are star and quasar. So now when we ran it, so we split the data into 70% for the training and 30% for the test. And when we ran this, what we found that accuracy was 73%. Now here we had to resort to the accuracy because we don't know the true value of the p. So that's why we cannot really calculate RUP square error. We had to resort to the accuracy. So Jacobi prior accuracy is 73.05, beating nearest to the Lasso 72.94. Others, yeah, they're pretty much doing as good as Jacobi prior, but Jacobi prior is marginally better. Whereas when it comes to implementation time cost, we are just simply 800 times, 900 times faster. So now naturally question comes, why Jacobi prior is doing so better than so we have not given any explanation in this paper. We just demonstrated in this paper that it is doing better. It is a method, proper method, without violating the standard Bayesian data analysis principles. because we are not, it is slightly alternative method because we are not eliciting prior directly on the data. We are eliciting prior basically on the another parameters and inducing prior on the data and use that to estimate data coming up with an analytical estimator, and that gives us much better. Recently, my friend and colleague, so I forwarded the paper to many of my friends, and one of my friends and colleague in IT Kanpur, S.I.W.S, he is a econometrician in economics department. He read the paper and he postulated a conjecture. The conjecture is, I think, so one day he just called me, Ashok called me and told me that I think what you are doing, your Jacobi prior is a generalization of Arnold Zellner's G prior. And I was a bit of a surprise. And I think right now I have a proof for that. But obviously, any proof requires a little more rigor, so we are working on that. That is our reason that why it is doing so well. So we have developed so I think another stock solution was Jacobi solution for the Gaussian process prior classification, and that was really like we were really surprised. Very good result, but because of the time constraint, I just thought will not do that. We also developed a method, we have proposed it in the paper itself, that partition data in distributed systems. So what happens if you have data all over the server, like 5 different servers, one server in Australia, another server in Singapore, another server in US, right? And you have terabytes of data, you don't want to bring all the data physically in one place. It's just humongous task, not possible. So we proposed a methodology that said that you do some analysis here, you do some analysis here, you do some analysis here, simple matrix manipulation. Just bring the summary statistics in the master server, which is much more less cost and doable, and then estimate your Bayesian estimate, the Jacobi estimate. So that also we proposed here. Our commitment is to open science. So every data, every code, every number we presented in the paper, we have made it available in the GitHub. Anybody should be able to reproduce our number. We are open to take challenge. Feel free to challenge us that, oh, there is a mistake. Please do let us know. And here are the references. Here's the QR code for paper and the GitHub repository. So please feel free to take this and enjoy, and do let us know how can we improve. Thank you very much.
Okay, questions?
One question is, can you also apply that to the type of problem which we of work was doing, like I think it's classification of classes? Would we be able to compete with the techniques that showing the CNN?
Certainly, we can try it out. I mean, it's the end of the day classification method, so we should compare it against all possible methods. We should compare, at least we should compare what the persistent homology techniques are.
Just a small query, maybe I might miss it. So basically here we are primarily talking about prediction. If we want to draw some inference, like which are the predictors important for the load of actually make the joint is posterior for betas. Is it accessible from here?
Yes, that is good. That is good. Why I'll tell you. If you want to get the posterior distribution, straightforward in that sense because because it's a transformation. So basically, if you know the eta hat, so from here you simulate from eta, plug it in here, you get the better simulation. You just put the next. That's all.
I have a very different question. So, for example, typically in regression problems in we assume that beta is sparse.
Right.
And here the thing is that the estimation may not be giving you a sparse solution.
Not necessarily. Not necessarily. So, okay. So we have taken the solution space sparse. Right. Lasso elastic was designed to have a sparse. Now here in this we are not saying that it will give you the sparse solution, but it will give you a solution which will give you a better prediction. So that is one of that indicative in this here that you can see that when it comes to RMSE of beta, so still these guys are much better. This because these produce a sparse solution. We don't produce sparse solution. It's a sort of a bias variance trade-off is happening. So, but here my prediction accuracy is better with respect to these guys.
So one more. Since you already have a closed form expression for this, can you have some kind of a test for the coordinates? That
Absolutely.
Then
Now it opens lots of problem statement because now you have a OLS status. So you can now basically regression enter it, you can take a textbook regression and take everything, whatever you want to just do that. Absolutely.
Thank you very much for the nice talk.
I request the chair to kindly present a token of appreciation to the speaker.
But the third talk is not yet. And in the system.
I now request Dr. Amyaranjan Bhome to kindly present a memento to Dr. Radhe Srivastava, Assistant Professor at IIT Bombay, as a token of our appreciation for gracefully chairing this session. Thank you to all the speakers for those deeply insightful talks. We now break for tea, which will be served outside the auditorium. Please rejoin us by 4:15 p.m. sharp for the next session on data science and applications.
और ये मीटिंग का
कहाँ बैटरी लो हो गया पूरा दिन। चाय पे क्या है? चाय पी के आना थोड़ा फ्रेश हो जाएगा। चलो बराबर हो रही है ना, इधर मिस्टेक नहीं हो रहा है ना। हाँ? ये रिकॉर्ड करना था क्या अपने को? करो ना रिकॉर्ड। नहीं किया तो फिर क्यों नहीं किया? इसी इनवाइट पे सब कुछ लगे नहीं, यूट्यूब पे रहेगा, टेंशन मत, यूट्यूब पे सब रहेगा। सीखेगा ना ये नेक्स्ट टाइम इसके ऊपर बुलाएगा ना इसको, यही तो रहता है वो। हाँ यही रहेगा अभी, वो नेक्स्ट ईयर तो रहेगा ही। उसको अभी केवी का नहीं नहीं नेक्स्ट ईयर आएगा, वो आएगा इधर। हाँ पता है ऐसे देखने के लिए। हाँ ये प्रोग्राम रे केवी का जॉब नहीं, केवी का नहीं टेक्निकल इशारा काफी हो गया उसको। मैंने नया एक क्या बोलते हैं लेकिन क्या अभी कैसे होगा टोपोलॉजी वाले से बात करेंगे। चलो कौन ज्योति मैम को ये दे दो ज्योति मैम ने
We now begin session 1T, focusing on contributed talks in data science and applications. This session will showcase a diverse set of innovative works in machine learning, cryptography, and mathematical modeling. It is my pleasure to invite Dr. T.S. Kulkarni from IIT Madras to chair this session. Professor S.S. Kulkarni retired in 2018 from the Department of Mathematics at IIT Madras. Following his retirement, he continued contributing academically at IIT Palakkad and IIT Dharwad. His research focuses on analysis with recent work on the continuity in Banach algebras. I request S.H. Kulkarni sir to please continue this session. Over to you, sir.
Thank you. Good afternoon. In this session now, there are 5 speakers in the session. So I request everybody to please speak the time, 10 minutes for presentation, followed by 2 minutes for question answer. First speaker is Anisha, second speaker, Arima West, Gradient.
Good evening, everyone. My name is Alicia. I'll be talking about ARIMA-based gradient prediction, time series inspired optimizer for stochastic regression problems. Give you a brief history about what we're talking about. First of all, in machine learning problems, our aim is to basically minimize the loss function. We want our predictions to be as close to our reality as possible. So that's why we have optimization. We want to minimize the loss function. So our aim in this paper is to use a hybrid novel idea of using stochastic gradient descent with ARIMA. Now, what are these things? I'll explain in a minute. So, so in optimization problems like SGD and Adams prop, the gradient sequence is often treated as independent and identically distributed. So we're basically overlooking potential temporal patterns, time series patterns. So in real life regression problems, there is noisy data, there is non-stationary data, and gradients exhibit a lot of autocorrelation. What we want to do in this paper is to capture those underlying temporal patterns. So we're using that, we're forecasting the next gradient using the ARIMA method, that's the auto-regressive integrated moving average method. We try to validate this approach with several regression tasks. Right now, for this paper, we've only dealt with linear regression, mainly because the loss function is convex. So that obviously makes our life a lot more easier in terms of the assumptions. But we hope to expand this to non-convex functions as well. So, as I said, we've dealt with the stochastic gradient descent. In very simple terms, it's two-level math where we differentiate the equations, equate it to 0 and find the point of possible maximum or minimum or saddle point. We want to find that point. Differentiating obviously is very difficult for a huge number of for a complicated formula. So what we try to do is we let the machine work for us. Now ARIMA, what it does is when we have data that is non-stationary, like for example, data that works like the stock market. We have a lot of jumps which keeps increasing. We want to have those jumps in a straight line. That's called stationary data. That's what we want. That's what ARIMA does for us. It uses different. It uses difference to make an upward trend in a straight line. As simple as that. So we treat the gradient in this case as a time series and forecast the next step using ARIMA. We try to improve stability and convergence in stochastic regression problems. So I'll give you a background of current gradient descent techniques. So batch gradient descent basically means we try to find the gradient using all the data together. That obviously is too computationally expensive, which means it takes a long time to find the answer. Stochastic gradient descent means out of all the data that we have, we pinpoint one random value, one random observation, and we do the whole process with just that one observation. And that obviously means that we have high variance and a lot of oscillation because we do not take the total data into consideration. So a compromise between both of these is the mini batch gradient descent, which uses batches like 32, 64, 128. Now this compromise does strike a balance, but it can also produce noisy updates and it only works on that particular current batch and it lacks awareness of what is going to happen in the future. And that's where ARIMA comes in. So algorithm is very simple. For a first batch of grade, for a first say K gradients, we use the normal stochastic gradient descent. And the remaining, we predict using those first K. And we use ARIMA on the first K methods. Now, the K that we have used in our empirical analysis is 100 because of Box and Zhao, that is the paper that was written by Box and Zhao, where they mentioned that 100 is a good, 50 is a good number, 100 is the best for predicting time series data. So what we've done, as you see over here, is we have a learning rate. We have a learning rate of theta. We predict a linear regression. We have beta 0 plus beta 1, simple linear regression. We find the loss function, reality minus the prediction, the whole square, and we want to minimize this function. So we, like I said, till k is less than equal, till the time is less than equal to k, we use stochastic gradient descent. We use that set of k gradients as a time series and predict the next batch of gradients using ARIMA. And we treat it as a time series. And we update theta, that is the parameter, to make it predict the future in a sense. So that's exactly what it does. So our main aim over here is to see how do the assumptions hold up. Do the assumptions of ARIMA and SGD hold up together because they are two completely different sets of where they arise from. So the setup is inspired by standard SGD analysis with added noise prediction model. So in our data analysis that we've done in the empirical analysis, we've taken 40% of noise. The 40% of noise we try to predict if whatever we have done is good enough or not. So these are our 5 assumptions. The first one is convexity, which is convenient for us in regression, in linear regression because it is convex. Second one is Lipschitz variance. So we have the theta, the L theta 1 minus L theta 2. It is the norm is the inequality holds up. The gradient is bounded. This is very important because we need to know that the minima actually exists. And the last two are ARIMA based noise properties. The first one is whatever noise we come up with, the epsilon t is unbiased. The expectation of epsilon t is equal to 0 and that the variance is bounded. Again, both of these guarantee that there is an actual answer and we're not just bouncing from one point to another. And there has to be a learning rate, that's theta t, which is what we start with. We ideally start with 0.01. And theta t over here is 1 by root t because that's a series that's convergent. And that's important for our analysis. We want convergence. So this is our loss function, and in our case right now, in linear regression, the function is convex and differentiable. There's a true gradient, that's del of L theta t, and there is a noise, that's epsilon t plus 1. They both add up and they give you the next batch of theta. So the new theta t plus 1 has an old theta t minus the learning rate into whatever the gradient that has been gotten from SGD and the noise that's over there. So our theorem predicts that under these assumptions, we have convergence. That's our point. So we assume that it is convex, in our case it is for linear regression, and it has Lipschitz gradients. if the Arima prediction error epsilon t satisfies these two conditions and the learning rate is theta t equals 1 by root t, then the expectation of L theta t minus L theta star is less than equal to C by root t. C is some constant. The root t is important because, like I said, that's the series that actually convergent. Hence, if it is bounded, that means our prediction also is convergent. The theta t over here, theta t bar is the average of all the thetas that we taken so far. So we have a mathematical proof of it. It's the first statement is as I mentioned, the next one, the next theta t plus 1 is the current one minus theta and the gradient. We take the difference of what we found minus what is our optimum. So theta star is what we want, right? So we want to find the difference, the norm of it, the square of it. We use the formula that we see in the first step. We expand it. We use inner product and we expand the particular formula. As you see, in the third line over here. So in the third line over here, if you see this, we have we simply just used a minus b the whole square, and we use the norm formula to expand it. This expands to two different inner products. So these two inner products over here, this one is equal to 0. This one is equal to 0, and this one is what we're dealing with. So as we go ahead, like I mentioned, this one is equal to 0. So this one vanishes over here. Over here, we have we've taken expectation on both sides. Now this is what we want. We want the expectation of L of theta t minus L theta star, because that's the one with the output, the minimum, the optimum value, and we have an optimum value over here as well. So we want to deal with these two together so that we see that it is bounded with 1 by root t. So when we see that, when we shift this over here, we have theta t plus 1 minus theta star and theta t and theta star. So what happens is you have theta 2 minus theta 1, theta 1 minus theta 0. So theta 1 cancels out and you have the end result and the first optimal result. And that's how we end up with this one over here. That's how we end up with this one over here. So all of this together, theta 1 minus theta star is all that's left. We take a summation on both sides and then we're left with this particular value over here and over here. This one is the constant, this one is 1 by root t. This one is the positive number. So the inequality still holds. So we have expectation of L theta t, the average of it, minus the optimal value is less than or equal to C by root. This tells us mildly that it is convergent. Okay, so this is sorry, sir.
Just find it.
Alright, sorry, my bad. So I just want to show you the graphs that we had as a comparison. So between STD and the Arima-based optimizer that we have, you see it's very, very close. This is the MSC loss. This is the difference between the mini-batch graded loss and the Arima-based what we have just predicted. This one was very interesting. Arima-based STD, batch STD, mini-batch STD, and STD, all of them together in one graph over here. This was very lengthy, very time-consuming. This took me an hour to get an answer actually, and these numbers come up to this. So as you see, comparatively, Arima-based STD is 170 for the NSC loss, is the least apart from mini-batch. So as compared to mini-batch, Arima-based STD works very well, and additionally it works as it's computationally cheaper for us to deal with. So, so our next step is to refine this further, and of course work with, more importantly, we analyze it for non-convex settings. Thank you very much.
Any questions? an example of L theta satisfying those conditions?
L theta satisfying this condition. You mean a function?
Yes.
Yes, this one. Oh. Yeah, this one.
Thank you very much.
Thank you.
Yes, thank you for this presentation. Very good. Next speaker is C in our one. Nullity and Cartesian operation on intuitions. So necessity and Cartesian operation on intuitions, fuzzy matrix, and Python. Hello.
Myself, Dr. C. Raghavan, Sri Thirumalai Science College. Good evening to everyone. I think my topic is the necessity of the Cartesian operation on understanding fuzzy matrix by using Python program. My topic is the concept of understanding fuzzy matrix was introduced as an extension of understanding fuzzy set, which was first proposed by Thirumalai in 1986. 1983. Why? Understanding fuzzy set handle membership and the non-membership. Understanding fuzzy matrix extended the concept of matrix allowing the application for decision making, pattern recognition, and optimization problem. But our paper is mainly focused. The necessity operation is inspired by model logic, particularly necessity and possibility operators used in fuzzy logic and rough set theory. The Cartesian product 1 to 11 are extension of a traditional set theory operation, but adapted for understanding fuzzy matrix. Basically the operation helps in constructing understanding fuzzy relation models. The basic definition of already there, the fuzzy set and the understanding fuzzy matrix. The understanding fuzzy matrix, Aij is equal to 1 indicating full membership. Aij is equal to 0 indicating non-membership. So 0 less than Aij less than 1 indicating partially membership. So another definition, understanding fuzzy set is also there. So membership and the non-membership is belonging to this 0 less than or equal to membership plus non-membership less than or equal to 1. So understanding fuzzy matrix, A is equal to Aij of order n plus n is a matrix where Ij is a membership degree of the element at the position Bij is the non-membership degree of the elements at the position I, j. The construction of each I, j is 0 less than or equal to membership plus non-membership less than or equal to 1. So See, this is our basic definition for our necessity and the Cartesian operation on industrial fuzzy. I think first one definition is necessity operation in the basic sets of a fuzzy set, and second one is the basic formula. So these two and define how to in Cartesian product 1, Cartesian product 2, and Cartesian product 3. So likewise, Cartesian product 5 to 11. So this is our theorem. If A and B be a two universal sets for every necessity operation of industrial constant matrix of this E and F, then the Cartesian product of one is also industrial constant matrix. So let us consider the 3 class 3 matrix or industrial constant matrix. Were different inverse E and F, and usually by using that AE complement and BE complement, again we get AE complement and BE complement matrix is also industrially fuzzy matrix. Again we can use necessity operation in A complement and B complement. Again A complement of E matrix and B complement of E F matrix is also industrially fuzzy matrix. These two matrices is applying the Cartesian product 1, it can like that. So how to find the cells x1 to x3. So x1 is equal to this using Cartesian product 1, and after that to finalize we can calculate this by using the Cartesian product 1 formula. Then finally we get the solution, and how to write a Python program for this 2D list of the tuples and formula of new comma b. Input the values A11 cells, actually float input A11 is equal to this, likewise, and B is equal to that, and C and D. So this is called A1 places, and finally we can A33 and B33, C33 and D33. So create a variable for first cell C11 is equal to A11. The first matrix of A11 cell is equal to A11 star C11 star. Comma again, because the in this fuzzy matrix has A1 comma B1. So like first cell A1 is equal to A11 star into the second matrix B matrix C11 star, comma A2 is equal to B11 star dot D11. So creating cells again x1 is equal to A11 comma B1. So input the values C11 is equal to x11. So similarly we can create a cell A11, A12, A13, 21 and 22 and 23 and 231, 32, 33. So finally the given output a necessity operation AE complement and BE complement is equal to this. Finally we get Cartesian product A1 is equal to this. So the Cartesian product 1 is also industrially fuzzy matrix. So our application of this necessity of the Cartesian product of industrially fuzzy. So decision making problem we can use IFMS. That means industrially fuzzy matrix helps model multi-criteria decision making problem where uncertainty exists. So medicinal diagnosis, optimization, artificial intelligence and machine learning by using IFMS. So risk analysis and forecasting, pattern recognition and text mining, transportation and traffic controls, engineering and control system by using IFMS, image process, cyber security, and environmental science and desert management. So this is our another theorems. So how to use Cartesian product 2 to 11, and also how to write a Python program in Cartesian product 2 to 11. So this is our future bar. Generalization of optimization. So algebraic structure on FMI, application in real world decision making, development of a Python program for IFMS operation. So incorporation of education degrees in learning machines. So computational analysis with other programming language. So integrate with the graph theory and networks. So dynamic or time varying IFMS by using. So this is our conclusion for model operator in fuzzy industrial matrix provide a structured way to handle the uncertainty in process and vagueness in the decision making, artificial intelligence, and computational logic. These operations extend classical models logic by incorporating overall the model operator in fuzzy and industrial fuzzy matrix serve as a value tools in modeling uncertainty environment between get gaps between classical and the real world application. So this is my reference. Thank you.
Any questions? Why are there so many definitions of partition product?
So we are already there, sir, but how to use in a partition product Python. So we can calculate that formula, sir. Partition product 1 to learn.
Okay, fine. Let's find this figure first again. Next figure is about new method for public key.
Good evening, respected sir and ma'am. I am Preeti Rao. Today I am going to present a research paper titled New Method for a Public Key Crypto System Using Smooth Transform of Linear Combination of Function. Before I start, I would thank to organizer and my guide, Dr. Anil Udekar sir. This is the agenda of today's presentation. Today we are living in information era where we need to keep information secure. Cryptography is one of the most important security control to secure information and communication techniques. When we send a message to someone, there is always a fear that some unauthorized entity either steal the message or modify it before reaching to destination. So, these techniques derive from some mathematical concepts and set of rule-based calculations called algorithm. Mathematics plays an most important role in cryptography. We use modular arithmetic, number theory, linear algebra. And in cryptography, the main motive of the attacker is to interrupt the confidentiality and integrity of the file. These are the attacks: brute force attacks, ciphertext only attack, known plaintext attack, chosen plaintext attack, and chosen ciphertext attack. This is the objective of study. We develop a new algorithm using mathematical concepts. These are some research papers that I have gone through. In first paper, G. Nagarashmi introduced a new cryptographic scheme using Laplace transform. Eureka extended this work for exponential and trigonometric function and also introduced the iterative method. Aditya introduced a new cryptographic method using linear combination of function. DS40 uses smooth transform. Eureka and I introduced develop a new crypto system using Ilzaki as well as smooth transform and develop a Python code for this crypto system. Akash Thakkar introduced a data security new crypto system using RSA algorithm and smooth transform. In this paper, we present a new public key crypto system by using smooth transform and RSA algorithm, a combination of three functions. And we generalized it and implemented it by using Python code, Python language. And we compare our encryption decryption technique using with other methods. These are the basic. This is the basic definition of smooth transform. This is the RSA algorithm, and these are the some series expansion. E raised to 2t, sin cos is 2t, and sin is 2t. We use these basic definitions and series expansion in our crypto system. This is our crypto system. Here we consider f of t function as a into p of e raised to rt plus cos h rt plus sin h rt. Here we use three functions, linear combination of three functions. First select the plain text p. First we convert the plain text into numerals by using ASCII code, we denote it as a PIK. After that, we take a smooth transform on f of t, and we get a pi1. pi1 is equal to bi1 plus p mod of 96 plus 32. Here we use Caesar cipher also. Means we add here p, and after that we pi1 is encrypted by using RSA algorithm. We choose integer g such that GCD of g with phi of m is equal to 1, and we find the secret exponent d such that g into d is congruent to 1 modulo phi of m, and here public key is m comma g and private key is d comma r a r p and li1 means our p. And exactly reverse process apply for decryption. This is the example. Here we take a plain text as word. Here n is equal to 4, and we convert this word into numerals by using ASCII code. Here we take a is equal to 7 and r is equal to 3. We put all these values, and we take smooth transform. Here we use a Caesar cipher, means we add value of p. Here we take p is equal to 13. And on pi1 we apply RSA algorithm. Here we choose g is equal to 23, and we find its secret exponent d is equal to 119. Our public key is 273, 23, and our private key is 119, 7, 3, 13, and 11. Therefore, our plain text word gets converted to ciphertext into these numbers. We include this method in theorem, such as the given n-long plain text in terms of pi1, pi of 0, where I runs from 0 to so on, can be converted to ciphertext pi1 under smooth transform and RSA algorithm. And this is the formula for pi1, and this is the formula for bi1. And our CI1 is equal to PI1 raised to G modulo M, where M is equal to A into P into R, multiplication of 3 prime number. And our key Li1 is equal to BI1 plus 13 minus PI1 plus 32 upon 96. Here we use ASCII code, and first 32 numbers are non-printable, so that's why we add here 32 and we take here 96. This is a generalized theorem. We can take any value of A, R, P here, and this is same formula. Just we take A, R, P instead of actual value. We take A, R, P. We can change the A, R, P value. This is a Python code for our encryption method, which gives ciphertext value of coefficient of correlation and execution time. This is the example. See here, our plain text word converted to these numbers. In first example, we take only capital letters. In second example, we take capital and small letters. In third example, we take capital, small, and numbers. In next one, we take special characters, and at the end, we take all the letters. Means capital letter, small letter, character, and numbers. The success of encryption method depends on the smaller value of R. So we compare here value of coefficient of correlation R. Here our coefficient of correlation value of our encryption method is less as compared to other ones. Next one is frequency analysis. Frequency analysis is one of the known ciphertext attacks in which we decipher the ciphertext by analyzing the frequency distribution of letters. By using RSA algorithm, frequency of plain text and frequency of ciphertext are saved. But by using our new crypto system, the frequency of plain text and frequency of ciphertext are different. This is the frequency analysis. In first graph, this is the frequency of plain text. In this graph, this is the frequency by using RSA algorithm. So frequency of plain text and frequency of RSA algorithm are same, and this is the frequency by using our new encryption method. These are the examples. Comparison with other crypto systems. In many asymmetric crypto system, the length of plain text and ciphertext are same, but in our crypto system, the length of ciphertext and plain text are different. Here we use a combination of Sumudru transform and RS algorithm. Means we convert a Sumudru crypto system using Sumudru transform to public key crypto system, and we develop Python code to get a quick output. And we use in this method we use Caesar cipher also. In this work, we develop a new asymmetric cryptographic system using a combination of Sumudru transform and RS algorithm of combination of three functions with Python code. In this method, the length of ciphertext and length of plain text are different. We extend this work for ASCII code and demonstrate successful application of paragraph encryption. We also extend this method for another language also, not only for English. We can use it for Marathi and another language also. And extension of this work is possible by using other suitable functions and other suitable transforms. These are the references that I have gone through. Thank you.
Thank you. Any questions?
Yes, sir.
One question is why you use the Sumudru transform. Second question, you made the combination of three functions.
Yes.
So, how do you choose that three functions?
Actually, sir, I have worked on. Actually, I have worked on Sumudru transform already because I have published a paper by using only Sumudru transform with two functions. So in this paper, I extend it for three functions, and we convert this symmetric algorithm to asymmetric algorithm by using RSA algorithm.
My question is why you particularly use the Sumudru transform? There are many more transforms are available.
Yes, we can use any one transform, sir. But I already worked on Sumudru transform, so that's why I use here Sumudru transform.
Thank you.
We can extend this Laplace transform also or Ilzappi transform also.
Thank you. Invite Chanchal Das to speak on computational geometry and mathematical.
Gopal.
Okay, thank you all, and good afternoon, myself Chanchal Das, and I am founder of a startup company, not exactly from academics, and my company name is Das Scientific Research Labs Limited, Private Limited, and we are developing a new way of teaching mathematics. So our main domain is math education, and this presentation is based on that. This computational geometry and mathematical modeling using MS Excel is a dynamic approach for math education. It is related to math education. So, why it is required? First thing, you see that mathematics is an abstract subject. We talk about this abstractness of mathematics, and we teach when we teach mathematics also. Then also we try to teach in abstract way. But for me, mathematics is abstract, but mathematics education is not abstract. So because you have to show, you have to tell the students that what it is it. So you have to demonstrate. Then you see this, we describe the mathematics, but in math education we should demonstrate. Till morning, you see, I have observed many of the presentation. Everybody describing the thing, and suppose I am not related this in this field, I will be blank. I cannot understand anything. But if you demonstrate what you are doing, then I can understand. Yes, oh, Banach space, it is like that, and something, something, something. Is not it? So our change should be there, not descriptive mathematics teaching, it is demonstrative mathematics teaching. And sometimes what we teach mathematical concept often rely static presentation. When Sir was explaining that multi-dimensional, he was trying to show and elaborate the dimension in different way. So we don't have any tool, isn't it? We try to explain by body language, you understand that. But how I can understand what you are meaning by waving your hands? So this is another thing. Then in class, what we do, every those are the students, they will be realizing that we have given problems, difficult problems in exam. Actually, what are those problems? It is for ranking only. It is not trying to understand your understanding in mathematical concept. It is they are trying to solve understand your problem solving ability. So this is also there. So we should stress on not on problem solving, concept understanding should be more. Then, due to this abstract teaching, many times we misunderstand this simple idea which is taught in early days. Determinant, if I tell anyone what is determinant, they will tell cross multiplication and then subtraction. But why? Why this number? What we get a number from determinant. But what is that number? Hardly any students and teacher can explain that. So similarly, why we learn limit? I teach for university faculties and I interact with the students. I conduct 3 days, 4 days, 5 days, 6 days mathematics workshops, and there are many university faculties join. I take the question, what is limit? And 100 people explain or define limit in 100 ways. So is it something, because we don't understand what actually limit is meant in calculus. Similarly, what is calculus? Calculus, what is that? If I have to tell a layman, sir, he may ask me, sir, why we learn calculus? What I should tell him? Is not it? You learn dy dx. Dx square by dx is equal to 2x. What will be the 2x? So all these are things not clear. And we live in dynamic world and we don't teach any dynamic tool for capturing the dynamism of this world. We still use usually on Newton's calculus. Calculus has become obsolete. the lot more technology has come. We can now avoid using differential equations, integration, differentiation. New techniques has come, but we are still struggling